Okay, well, a couple things before we start. We're going to meet now. I think for the rest of the semester we can meet face to face. So starting next week, next Thursday, you'll come up on campus and you'll meet face to face. You want to, if you guys have a digital multimeter, you want to bring your digital multimeter with you. Pretty much every time you come to class, have that with you. Not saying we're going to use it all the time, but you want to have it available. We have a couple assignments. Some were uploadable, some were not. I think there was a video on Tesla, which was uploadable. You should have looked at that by now, and I don't know when the link probably expired already. I don't know if you can still upload that or not. But there were a couple labs. Lab 1 was something that you did. I think it's a packet that deals with calculations of complex numbers. You had a couple weeks now since the beginning of the semester. On purpose, I didn't want to take that one right away. Typically, it takes students 2 to 3 weeks to get through that, so at least 2 weeks. So you've had plenty of time to do that. I decided I'm not going to have you upload that. I'll have you actually turn that in, and I'll go through and I'll just kind of check it off to make sure you did it, and I'll give it back to you. Lab 2, same kind of thing. Lab 2 is you watch a video and you define some terms. There's no way to submit it, so I'll have you bring Lab 2 and Lab 1 in with you when you come in next Thursday. Now, if you got my announcement, I actually put up another lab tonight, Lab 3, and that Lab 3 is due on Sunday. I decided I wanted to do something on generator action. Typically, we don't cover that in lab, but I think it's important enough to where I'm going to just kind of add that to the course. So if you got a chance to look at that, this shouldn't be too bad. Allow yourself maybe an hour or so to do that lab. It's due Sunday, this coming Sunday at midnight. So take a look at that when you have a chance. If you have any questions, you can send me a text, and I'll be happy to answer them. But I do think the lab is pretty straightforward. There's a homework 1, which was a sheet that you should be able to do after we talked about AC voltages and waveforms and sine waves. So that one you can bring in. I'll just put a list up on Blackboard of what you can bring in with you when we start class on Thursday. Now, what you'll probably end up having on Thursday when you get here, I prefer doing face-to-face quizzes, and so I'll probably hit you with a quiz when you come in. So what I'll do, I'll put up just kind of a little study sheet, because we've covered a lot of stuff. I mean, what do you study? There's a lot. So I'll put up a little study sheet, just kind of narrows down what I would expect you to do or to know for a quiz if you came in on Thursday and I gave you a quiz. So face-to-face, and I'll put up the room number and all of that before next week. And if you have any issues or questions, feel free to send me a text, and I'll respond to that as soon as I can. Does anybody have any questions for me before we start? We got a lot of material to cover tonight, so I want to jump into it, but any questions?
Yes, Professor.
Yes.
About Lab 3, I think Sunday is so early. Why not like a Tuesday?
I'm not understanding what you say. I heard you say Lab 3, and that's all I can make out.
I say Lab 3, to do it on Sunday, I think it's so early. Why not to give us like a Tuesday?
Have you read it?
They do it of the Lab 3 on Sunday. Yeah. I think so early. Why not Tuesday?
Yeah, Lab 3 is due Sunday night at midnight. And I'm asking you're asking me why can't you have it due on Tuesday?
Yes, please.
Have you read the lab? Have you looked at it?
I have opened it already.
Yeah, it's something you should be able to do in less than an hour. So I don't really think I'm not going to argue over a due date. It's not a lab that you're going to spend a lot of time doing. So you guys look at it, and if for some reason you think Sunday night is out of the question, let me know. But I think if you look at it, you'll see that it's pretty straightforward. It's not anything you have to spend a lot of time with. So I'm going to leave it as it is, and unless some other people ask me about that. But hopefully you don't find that too difficult. Look at the lab first, and then you can make comments about it before you ask me to do something like that. I'll have you open it and look at it.
Okay.
Let's go ahead and get started.
I got a question.
Yep.
I don't know
Sure.
if it's me or every time I try to open Lab 2, it just come up blank and say untitled. So I don't know if anybody has that problem.
Does anyone else have that problem? Okay, who is that talking now?
Abdul.
Abdul, I will during the break, when we take a break, let me check it. Let me look at Lab 2 and see if it's something on my end that I can do. So
Okay.
there should be a link. Yeah, there should be an attachment that you can click on, and it should open up a Word document. And I usually don't have any issues with students opening that up, but let me check my Blackboard, because honestly, all I did was copied it from the last course over. Maybe something happened, I don't know. I'll check it out, and during the break, I'll get back to you during the break here.
All right, thank you. Because it's the same problem with Lab 3 as well. So.
Really?
Yep.
Can you check your Windows system or Google?
Is anyone else able to open up Lab 2? I'm just curious.
Yeah.
Anyone else
I've been opening.
You can open it, Mike?
Me too, but.
Oh, interesting. Abdul, what kind of computer are you using?
I'm using a MacBook.
Don't ask me why I'm laughing, but okay. All right. Well, let me see, because what I can do is I can, as an instructor, I can take my Blackboard and turn it into what you guys will see. So I can look at it in an instructor's view, or I can change myself to a student. So what I'll do is during the break, I'll change it to a student. And tell you what, if it seems okay on my end, Abdul, that means it's probably something, I don't know what it would be. What I can do though is open it up. Now, are you able to, you're just saying you can't open the document, right? You can't open the document?
Right.
Okay, so I don't know how I have it saved. I'll save it as a PDF. You should be able to open up a PDF on any machine. So we'll experiment during the break. If I have it saved as a document file, Word file, I'll change it over to a PDF, and I'll have you see if you can open it at that point. If you can, then you're teaching me something, because that means that people with MacBooks might have some kind of an issue. Somebody sent in a text. Let me see. Michael might have trouble with Google browser. Michael says you might have trouble with a Google browser. Email it to yourself and then open it. Somebody else says, Michael, is it Michael? Mr. Meyer, is it Mansell?
It's Mandy.
Mandy, I'm sorry. Mandy, I wear, you guys don't know it, but I wear glasses. I can't see anything anymore. So I'm just acting like I'm still young right now. So sorry, Mandy says, email it to yourself. So experiment with some of that. Email it to yourself and see if you can open it. And Abdul says he'll try it. Okay, so we'll try it, and then I'm also going to save it as a PDF. Normally what I do is I save everything as a PDF, because the PDF, in theory, you can open it up on any machine. But the only reason I save Lab 3 as a Word document is because when you read the procedure, you just kind of read it and follow along. And then there's certain questions I ask in the procedure. I want you to actually type it onto the paper that you're reading, and then change the font color so I can see, I can see the difference between my questions and your answers. So I left it as a file that you can type on, a doc file, docx. But if it's an issue, you can print it out and you can handwrite it or type it on another sheet of paper. It's not a big deal. I mean, you guys, if this were DC, I'd probably be a little bit more of a stickler for things, but you guys have been punished enough probably through DC, especially if you had me for DC. And then we'll be a little bit more lenient here. So if we can't get it open, worst case, we'll do it. You can bring it in next week. I mean, that's not that big of a deal.
Please, Professor.
Yep.
Yeah, there's something here I can see. It looks
Michael,
like
Michael, what kind of microphone are you using? Because this sounds so bad. I think I had this issue with you last semester.
Okay, maybe let me find the What? Something to use here. Maybe it's gonna work now.
I can't understand. I'm sorry. I can't understand anything. It sounds like you're talking in a tin can
I don't know
to
why.
me. I don't either. Can you guys hear Mike okay? Is it just me or is it everybody?
Hello, can you hear me now?
It sounds a little better now. What'd you do?
I just put earphone.
Your headphone? Yeah, that sounds better. Now ask me your question again.
Yeah, it's looking like you ever give us a sheet, yeah, for topic sheet. In the end, you put like a homework too,
Uh-huh.
chapter 15, but we cannot find this page,
No,
689.
okay. Yeah. So that's actually, I'm glad you brought, that's a mistake because I think I gave you guys an extra, normally what I do or what I used to do is put all the homework on the end of the topic sheet. So then you have like 10 different homeworks in 10 different folders. What I decided to do was move all the homeworks to a homework folder. So there's a homework folder on Blackboard now. I want you to go to one place so you can see what your homework is and when it's due. What happened was when I moved that topic sheet over that you're talking about, I forgot to delete the homework off of that page. So just ignore that. What I plan to do is I'm going to make a copy of my book and I'll put it up on Blackboard so you guys will have a copy of those problems to do. Okay, so don't worry about homework 2. I'll post that up in the next couple of days.
Okay, understanding.
Okay, so guys, hold on. If you have any more questions, let's hold them to the end of the. I was going to say the end of the semester. That would not be good. Hold them to the end of the period today. And I want to get into the material. It's like 20 after now, and we got a lot of stuff to talk about. So let me get into the material. If you have a question, just please write it down. At the end, when we're done and we're packing up to leave, I'll stick around and I'll answer any questions or talk about anything that you might not understand. So let's do it like that. And Michael, that lab, I think you guys, if you look at that lab, it should be pretty enjoyable. It's a very interesting lab. So it's not anything that you guys spend a lot of time doing. You know, just like an hour is probably all you need, or maybe even less than that. But you'll probably find yourself, it's kind of fun to do. So you might find yourself spending a little more time just because it's kind of fun to do. But we'll see. We'll see how it works out. So let's kind of go over where we are right now. And actually, we spend a lot of time talking about basically physics of AC. We call it physics of AC. So all of this stuff that we talked about last week and the week before, if I wanted to, I could have just started with the sine wave, what that voltage equation looks like for sine wave, script V equals VP sine omega t. I could have just started, a lot of books, a lot of they start right there. Not too often they go into all that detail we went to understand what that stuff means. The reason I do it is because I find that later in the semester, when we're dealing with certain concepts, if you have a physics background, at least the AC part of the physics background, you'll understand that stuff in much, much greater detail. So I kind of like to go into the depth that we did. Do I expect you to understand 100% of it? Probably not. But if you get something out of the last 2 lectures, then I'll consider myself having done my job. The videos are available. You can go back and rewatch them, relook at them, or whatever. Now there is one negative to this whole thing of meeting face to face, and that is I have this one camera, and I think we're in room 4 something. I'm not sure, but you're probably going to lose the ability to. I'm going to probably lose the ability to record. I don't want to move this camera around from face to place. It's been sitting here for almost 2 semesters now, and I don't think it was a good idea for me to keep moving it. So I don't know that after we go face to face, I'm not sure that I'll be able to record the lectures anymore unless I can come up with something else. I actually do have another camera. When we first went on the web, I bought 2 cameras. One is a backup. I've never used a new one, so it's hanging in my basement right now. But I spent a lot of money trying to get this stuff so we can go mobile and go live on the web. So I don't know if I may see if I can get another tripod. I like the fact that you can go in. If you miss a lecture, you can go and rewatch it, or if you want to go back over something, you can play the video. I really like that. But typically when we go face to face, I don't record. I'm all over the board too. Like the camera, I have trained on just part of the board. Well, when you're in class, I use the whole board. This is kind of impossible to do that. So I don't know. I'll think about that some more, and we'll see. That's the only negative I see to going coming back face to face. Although I will say this course is much better when we're all here together with each other. And I asked for this course to be face to face and not web. I just did the web thing because the COVID numbers were so high, and my mom, she has issues. She has a bunch of different health issues, and I'm her caretaker, and I couldn't take a chance. But she's gotten the first of her vaccines, so I feel good about that. The numbers are dipping down, so I feel good about that. And I know you guys are going to mask up, and we're going to be as safe as we can, so I feel good about everything. So we'll see how it works out. Anyway, let's get into the conversation I want to talk about. So we talked about AC, why we need it, what it is, why we need AC and DC. We went in and we looked at on the board how an AC generator is constructed. And from that generator, we were able to determine the type of AC waveform that you would get. There's three. There's sinusoidal AC. There's a triangle wave that is AC. There's a square wave that's also AC. We looked at those three forms of AC, and we said, all right, if we have a rotating machine, if we have a machine that uses Faraday's law to generate an AC voltage by rotating the coil instead of going like this, like we did in the very first video that you watched, what kind of waveform would that produce? And just kind of using the idea of a phasor and just some logic, we were able to determine that it has to be a sine wave. And the fact that we already know the mathematical properties of a sine wave made it easy for us to come up with an expression to represent an AC waveform. And so we had to take that expression, massage it, and do a few things to it. But we ended up with an expression for the AC waveform that takes into account the instantaneous value, the angular velocity of the generator that creates the waveform. We talked about frequency and period. There's a whole bunch of stuff that came out of that conversation. So that type or that way of representing an AC waveform is called time domain. Time domain. And I think in the last class I explained why it's called time domain. So what we want to do today is we want to talk about another way of representing an AC waveform. It's called phasor domain. And we kind of defined the phasor, but I'm going to tell you exactly, give you more information on what a phasor is tonight. So that's one of the things I want to do is talk about the different way we're going to represent. Typically, if you want to look at the mathematical properties of an AC waveform, you show it in time domain. But when you want to do calculations for the AC waveform or AC quantities, then you want to write it in phasor domain, or at least write it as what we call a complex number. So tonight we're going to spend time talking about types of numbers we use in AC. We'll talk about complex numbers, and we will also talk about phasors. And at the end of the last lecture, I also mentioned when we talked about different ways you can write an AC value, you can write the peak value, the peak to peak. There was one called the RMS value or effective value. And I mentioned to you that I would tell you in this class, when we say RMS, what exactly do we mean? What exactly is the meaning of an RMS value? So I want to go into some detail there. And again, I'm going into more detail than most professors probably would, but I find if you understand what RMS is, then you'll know why you're using it, number one, and then it'll make some other things down the road a little bit more clear. That's why I'm taking time to do this. So that's going to be what we attempt to do tonight. We'll see how far we get. And the fact that you're doing that lab, it's a virtual lab, means that I got a little bit more to do with my time. Normally we'll lecture for like 2 hours and we come in the lab. But now, since the lab is just something that you can do at your leisure, we should have a little bit more time to talk about the theory stuff. So now, I don't know if you printed it out or not. Michael was referring to the topic sheet. He was talking about the homework because I have the wrong homework. It's the right homework, but he was saying it's the wrong page number because you guys have a different edition of the book. So if you got this, it's on your screen now. I'm sharing it with you. And guys, by the way, in the upper left-hand corner of your screen, there's a square box. If you mouse over it, it turns into a magnifying glass. You can click on that and you can zoom in on that document. But what Michael was referring to is at the bottom of this page, you'll see homework 2. So usually in the past, what I would do is every time I have a topic sheet that I handed out to the students in class, at the bottom of that topic sheet would be a homework. And every topic sheet had a homework assignment and a due date on it. Now, I stopped doing that when we started doing this online stuff because students they would get confused on what was due and what it was just confusing. So I decided I would just make a homework folder and put all the homework in there. But what I did here, I just copied this from another class I taught in the past, and I forgot to take that homework off there. So you can just ignore that. Those are the actual problems, but if you have the 10th edition of the book, your problems might not line up with these, because this is taken out of the 9th edition of the book. So what I'm going to do is this. I'm going to make a copy of my book, and I'll put it up on Blackboard in the homework folder. I'll title that homework 2. It'll be these same problems, and then you can just use that sheet. The reading is the same, the 9th and 10th edition of the book. So you can read your book and just do the homework problems that I have listed on my sheet. And I do have a 10th edition of the book. I could change these problems, but I just don't have time to do that right now. So I prefer to make a copy of the problems out of my book. You read your book, and then just click on the link to open up the problem page. You can do the problems. And I will also provide the answers to the odd number problems. So, but anyway, this is the topic sheet. There's 2 topic sheets tonight. There's one on complex numbers, and there's another one on phasors, and we need to talk about both of those tonight. So this is the one on complex numbers, and if you're following the book, which you should be doing, if you're reading, you want to read chapter 15. So we're now in chapter 15 of your textbook, and the subject there will be complex numbers. So if you're looking at this, and I don't know what this is. It looks like a little Z right there. I don't know what that is. What is that Z there? It must be some kind of typo. See in the upper hand, and right here is like a little Z. I don't know what that is or why that got there. But anyway, I want to start by talking about complex numbers, and I'll come back to this sheet in just a second. So normally when I talk about this subject, I tell students this. For the next hour, I want you to forget everything you were taught about numbers. Just act like you don't know anything about numbers or number systems. Okay? Some of you really don't, so it won't be an act. I'm just joking. But really, no, seriously, just forget for now everything you know about numbers. And why am I saying this? Because this could be, the lesson that we're going to go through tonight could be really easy or not so easy. It's not so easy for adults because you're always trying to tie to something that you don't really know, or you're trying to tie to something that you already know, and it just doesn't make sense. Just kind of follow the logic of what I'm saying and accept it. I mean, it's true. What I'm telling you is going to be true, but just accept it. And then as you use it later on in the semester, when you start using it, the whys of that, you might ask, well, why is this true or why is that true? The whys will become self-evident. So just kind of accept what I'm saying and try to understand what I'm saying, and don't try to tie to anything else to make sense out of it. Just accept what it is, and it'll become clear later on in the semester, I guarantee you, because that's what happened with me. I'm not in the class like, wow, what does this stuff mean? Why are we using this? But then when I start actually working with it in engineering courses and physics courses, then I understood why it was necessary. So I'm going to ask you, just forget what you know about number systems, and we're going to just kind of act like we're going to teach you number systems all over again, just about numbers in general. So when we learn about numbers, we always like to start with a line, and this is called the number line. And when I make the number line, what we usually do is that we will put an arrow over here, and we put an arrow over here. And of course, you know that those arrows, they mean that it's actually a line, because if I draw this, that's not really a line, is it? Yeah, in geometry, that's not a line, that's a line segment. In geometry, if I have a line, I actually put these arrows on it. Well, one arrow won't do it because that's not a line either. In geometry, that's a ray. All right. If I want a line, I I got to put an arrow on both sides of it. And all that means is that line extends, because in geometry, a line extends in both directions and it's infinite. So this one right here goes towards positive infinity, and the other one goes towards negative infinity. So you know that just from the picture. No big deal there. So I'm not going to worry about the infinity part. I am going to worry about the negative or positive part. So but before I can do that, talk about negative or positive, I got to put a mark on the line that I'm going to refer everything to, every other point on the line to. I'm going to put a mark, and you can put it anywhere you want, but typically because it's more aesthetically pleasing, we put it in the middle. I'm going to put a mark in the middle, and I'm going to call that the origin. And the origin means that we're going to refer everything to this point. It's our starting point, and so we give that a value of 0. Once I do that, once I set the origin, then I know if I'm over here to the right of the origin, I got bigger and bigger and bigger quantities, bigger numbers in the positive direction. If I go to the left of the origin, I get bigger and bigger numbers in the negative direction. So I have this negative and the positive. And I want to talk about the negative and positive sign. That has a certain meaning. Now you kind of know what it is, but they really didn't teach it to you. Well, they taught it to you the right way, but they didn't teach it to you the right way for engineering, electrical engineering. So we're going to kind of unlearn some stuff and then relearn it. So everybody pretty much have seen this number line. And then once you get the origin in there, what you can do is you can put tick marks, and if you make them evenly spaced, you can represent any value you want to, any number. So I can just put these evenly spaced tick marks, even from the origin. And I can go back the other way. Of course, these go on and on and on in the negative direction and positive direction forever. So now once you do that, what you can do is you can plot the magnitude of a number. You can plot the magnitude of a number. So nothing I told you so far was new. Everything you know, I might be saying it a different way because I'm not a mathematician, I'm a physicist, but still, you've seen this before. If you want to plot a point, let's say I want to plot the number 3. If you want to plot the number 3, here's what you would do. I would go 1, 2, 3, and I'll put a point right there. So I can plot the value of the number 3, but there's another 3. I can also do this. I can go 1, 2. I can put a 3 over here too, because this value is 3, and this value is 3. So how do I distinguish one 3 from another? Matter of fact, for every value over here to the right of the origin, to the right of 0, I have the same value over here to the left. So how do I distinguish the left values from the right values or vice versa? Of course, you know that if I'm on 0 and I go to the right, and that 3 is not the same as that 3, because this really right here is a positive 3. And this right here, what that really is, it's a negative 3. So even though the number 3 is the same, really we're talking about two different numbers, because this is positive 3 and this is negative 3. Well, the positiveness or negativeness of a number has another name that you may or may not be used to. It's called phase. All numbers have phase. Now, this is the part of the conversation in the number line you probably haven't heard before. Most students haven't heard what I'm about to say. But in nature, all numbers have phase. And the way to think about phase is this. There's two ways I can get to positive 3 or negative 3. There's two ways. I can either do what I did before. I can just start at the origin, and I can go 1, 2, 3. So that has a magnitude of 3, but this right here represents the phase. I don't know if this green, this is like a fluorescent green or something. I don't even know if that's showing up in the camera. Can y'all see that green? Can you see that? Is it too light?
It's too light.
I'm not going to use this anymore. I don't like this. Last semester in my AC class, my students really enjoyed that class. And so they bought me as a gift a bunch of, because I only had like four marker colors. They bought me this is like 12 different colors of markers. So you see I've used most of them. And this green, some of these lighter colors don't really work. I like the color code and everything, but I don't know what the camera picks up. Like if you in class, this will probably be okay. And then the camera, I don't think this is a good idea for the camera. So I'm gonna retire this one. When you'll see this one again when you come to class, I'm gonna use something that shows up a little bit better. So what I wrote was this: that positive 3. What you have here is you have that part right there, which is called the operator. And that tells you the phase. That has to do with the phase. And then this is the size or the magnitude. And the same with this. This is a -3. So again, that's the magnitude. And then that minus sign represents something called phase. Well, you might think to yourself, well, hold on a second, Singleton. Just hold on. How come I haven't heard of this before? If this concept or this ideal of phase exists, why is this the first time I'm hearing about it? And the reason is because probably for everything you've ever done up to this point, you didn't really need to know about the concept of phase. Most lay people, most non-scientific people or non-engineering people, they don't really need to know about this concept of phase. So what they did, they hid it from you. They hid the idea or concept of phase in this plus sign and then the minus sign. And here's what I'm talking about when I say that. What we mean by phase is you can take basically a directed line segment. A directed line segment is just a smart people way of saying an arrow. An arrow. You can take an arrow because there's two ways to get to this point. I can go out. I can just start at the origin. I can go 1, 2, 3, and I'm there. But the other thing I can do. Hold on. Let me get a prop. The other thing I can do is I can take an arrow that's like one unit long, and I can stretch it out by multiplying it by a certain magnitude, like 3. And so I get this arrow that I'm going to put right here, and that arrow is able to, I can flip it this way, or I can flip it that way. I can flip it that way or that way. And with the arrow, if I know what angle to turn it to, either 0 or 180, if I know how long to make it, that's another way I can get to this point. So what I'm saying is, I can write this value right there. I can actually write that as positive 3, and that would be my phase. Or I can say, all right, I got this directed line segment, a phasor. It's an arrow, and that arrow is 3 units long, and it makes an angle of 0 degrees with the positive axis, Let's see, x-axis with the axis. So in other words, I can write this. This is 3, and then this sign right here. I don't know if you've seen that in math before, but that stands, the way we say it, at an angle of. 3 at an angle of, and then we will write over here 0 degrees, and that is what I mean by phase. So you might say, well, I've never seen nothing like that before. And I would say, well, probably right, because you never took AC before. In AC, we got to use this stuff, and you'll see why, by the way. I'm not just throwing this out. You're going to understand exactly why we need this. So what I'm saying is, when you say positive 3, what you mean is the size or the magnitude of the number you're talking about is 3, and the phase is 0 degrees. That 0 degrees represents a directed line segment, a phasor that's pointing to 3, and it makes an angle of 0 degrees with respect to the positive axis. Well, what about negative 3? Well, negative 3 is exactly the same in that the magnitude is 3. So I would write it as 3. The magnitude is 3, but when I use that directed line segment, I got to take my phasor now, make it 3 units long, but I got to move it over to point to that 3. So I got to move it over this angle now. This angle is 180 degrees. So when you write negative 3, what you really mean is 3 at an angle of 180 degrees. That's going to look like 180. So this ideal or concept of phase is often hard for students to swallow because you've never seen it before. Like I don't really think. Well, yeah, all numbers have phase. All numbers have phase, but it's usually when you do like accounting or just in regular people that use regular numbers have no need to know about phase. So they hide this phase angle in that positive sign, and they hide this phase angle in this negative sign. And what I'm telling you tonight for this class, what I want you to do is when you see the number positive 3, I want you to think of 3 with a phase angle of 0 degrees. And when you see the number negative 3, I want you to think of 3 at an angle of 180 degrees. This right here is a phase angle. And the way we represent that phase angle is I can use a positive sign to represent a phase of 0. I can use a negative sign to represent a phase of 180. So that's the first thing I want you to wrap your mind around tonight. Now, in math, there's something called an operator. And you know the 4 operators. You know what they are. The operator, here's an operator. So there's this operator. There's this operator. There's this operator. And there's this operator. Now, what operator is that? What is that? What operator is that? Did you guys fail 2nd grade? Tell me what operator that is. You know what that is.
Addition.
Right. Addition. Now, these are all binary operators in the sense that you'll have a value over here and a value over there. That's addition. So that operator, what an operator in math does is it tells you what to do with 2 numbers, 2 or more numbers. And we kind of just by learning through experience, we know that what this means, it means to add them up. So this is the operator that means to add. That means to add. And this is the operator that means to subtract. And this is the operator that means to multiply. And this is the operator that means to divide. So we all know that. I mean, it's no rocket science there. So we know that. But now you got to be careful because this operator and this operator are actually used in 2 different ways. See, when I have it like this, if I have A and then that operator, that means add. Or if I have A and then this operator, that means subtract. That's different than this operator and this operator, right? It's different because this operator, when it's between 2 numbers, means to add. This operator, when it's between 2 numbers, it means to subtract. But what I'm telling you is this operator, when it's in front of a number, means that the phase is 0 degrees. And this operator, when it's in front of a number, means that the phase is 180 degrees. So the takeaway is this, that this sign, you got to look at where it is. The placement of the plus or minus sign between 2 numbers, when I'm using it as a binary operator between 2 things, 2 numbers, and that means to add or subtract. If I use it by itself out in front of a number, like if I have a negative 10 here, then what that means is 10 and my phase angle is 180. If I write it as a positive number, that means 10 and the phase angle is 0. And you know for this one, I don't even have to write that. It's understood to be positive 10, so the phase would be understood to be 0. Normally, you don't think or write phase this way. You don't have to because when you're adding, subtracting, doing regular non-scientific, non-engineering stuff, you have no need to know about phase. But guess what? We do. We got to use phase. Okay? So that's the first phase. So does anybody have any questions on what I mean about phase?
I have a question. The question is, it's only 0 and 180 degrees. There's no like 90 degree, no.
There actually is. That's my next step.
Oh.
But I want to know about this. Who is that talking?
Daniel.
Okay, Daniel. Daniel, you're just a little bit ahead of me. There is.
Oh.
I'm thinking ahead. No, that's fine. I like when students do that. But that's my next step. I just want to know. See, when we count, God, listen. When you count money in your bank account, when you do calculations, you're basically dealing with numbers on the number line. And most numbers in nature that you would have to deal with as a layperson, a non-science or non-engineering person, this is fine. But God played a trick on us. God gave us certain quantities in nature that don't exist on this real number line. That's why we need another number system, and that's what I'm getting to. So let me ask the question I asked before. What I'm talking about so far, even if you don't accept it, I really don't care, because like what's that, that Tyson physicist dude? He says science is true no matter whether you accept it or not. So I don't really care if you accept it. It's true. The question I have for you is, do you understand what I'm saying? Does everybody get that? Let me just make this real clear. That I'm going to have the operator and I'm going to have the phase. And what I'm saying is, when you see a plus sign, the phase angle associated with that is 0 degrees. When you have a minus sign, the phase angle associated with that is 180 degrees. But that's only when it's used, not like this, but like if I had something like a minus A or a positive B. Now I'm talking phase and the magnitude. And everybody should be shaking their head. Even if you don't like it, you can at least understand it. I know you can, because I actually showed this to some 7th graders one time, and they got it. Like, they don't really try to connect it to anything else. I could just tell them unicorns exist. They believe anything I say. So it's a lot easier to teach younger people, because they don't try to make sense out of it as they go along. They just accept it and they use it, and then the understanding will come a little bit later on. And that's the same thing that'll happen to you. Okay? Now, so Daniel brings up a good point. He said, okay, that makes sense, but can we extend this to other angles? I mean, is there only a phase of 0 and 180? Are those the only two phases? And the answer is no. No, there isn't. There actually is this. It turns out that just like the phase angle of 0 comes up a lot, and the phase angle of 180 comes up a lot, they come up so much that we gave them their own operators. We gave them the operator a plus sign to be in the phase of 0, and the operator minus sign to be a phase angle of 180. That comes up so much. Well, in engineering and science, another angle comes up a lot. Another angle comes up a lot. The phase angle 90 degrees and minus 90 degrees. And, just so you remember, minus 90 degrees is really 270. So minus 90 degrees, or 90 degrees, the phase angle of 90 degrees, and 270 degrees, or minus 90 degrees, it comes up a whole lot. It comes up so much in AC that they gave it its own operator, just like this. They gave, let me draw the picture and you'll see. It's better to look at the picture. That angle of 90 or negative 90 comes up so often in AC that they gave it its own operator, just like they did 0 and 180. So now we got to do this. We got to have two axes. We got to have an axis like this. Now I'm going to name this as I go along. So in math, you already know what that is. This is called the real number line, because there are real numbers on there. So this is the real number line. And most numbers that we deal with in nature, counting, banking, whatever, it's going to happen on the real number line. But just imagine numbers that don't happen at 0. Now, it's hard to imagine that. It really is hard to imagine that. But kind of imagine numbers that don't happen at 0, or imagine numbers that don't happen at 180. Imagine numbers that happen at like 90 degrees. Or imagine numbers that happen at like negative 90. Imagine this. What if I have those numbers and I call those imaginary numbers? Ooh, I like that. Let's call these imaginary numbers, because it's hard to imagine these. Now, that's kind of slick. I like imaginary numbers. Imagine this, imagine that. Now, there's only one thing about using that term imaginary. When when I use the term imaginary, what do most people think? I mean, honestly, what do most people think when I say imaginary? What do you think?
It's not real.
It's not real. Most people think it's not real, but let me assure you of one thing. If you take your real finger and stick it in an imaginary 1,000 volts, you're dead. There's nothing imaginary, there's nothing not real about what I'm going to talk about. So when I say imaginary, I don't mean like unicorns and mermaids. That ain't what I'm talking about. These are real quantities that exist in nature, and it's the whole foundation of what we're going to talk about in this class is based on these numbers right here. So because I'm using imaginary, don't think not real. Oh yeah, they're real, as you'll see. They're real. All imaginary number is this. A real number is a number that happens to have a phase of 0 degrees or 180 degrees. An imaginary number has phase of 90 degrees or minus 90 degrees. And so we have this axis right here. We have the real number axis, but the one that's going to represent 90 degrees or minus 90, we're going to call that the imaginary axis. So any point I plot on the real axis is a real number. Any point I plot on the imaginary axis is an imaginary number. And all that means is, if it's on this axis, the real axis, the phase is either going to be 0 or 180. If it's on this axis, the phase is going to either be 90 or negative 90. That's all it means. Again, don't worry about why. That'll come later on. Just accept it. So, just as I can do this, I can say 1, 2, 3, 1, 2, 3, and I can put a point on this real axis. I can put a point right here to represent positive 3, or I can put a point right here to represent negative 3. I can do exactly the same thing on the imaginary axis. I can do this. I can say, all right, I got 1, 2, 3, 1, 2, 3, and I can put a point right here on the imaginary axis that represents 3, and I can put a point right here on the imaginary axis that represents 3. But how do I distinguish the phases? How do I do that? You see right here, the phase for this one, we represent that with a positive sign. And like with this one, the phase for this one, we represent with a negative sign. But how do I represent a phase angle of 90 degrees or a phase angle of minus 90 degrees? And so what they decide to do, they being the math people, I call mathematicians math people. I have a physics background, and we always get into it with the math and the physics people always kind of go back and forth in battle, so we call them math people. Sounds like something from a different planet, the math people, but anyway. But look, what I'm saying is this. Just like I want to write the operator and then the magnitude, I want to be able to do the same thing when I have a phase of 90, and I want to do the same thing when I have a phase of minus 90. So how do I do it? Well, the math people say, all right, you know what I want to do? Let's use this. We're going to use the letter I. And so if I have a plus I, that means the phase is 90 degrees. And the minus I, if I have a minus I, that means the phase angle is minus 90 degrees. So over in this list, I can add to this. I can put for the operator plus I can say, all right, that phase angle is going to be 90 degrees. And then the minus I, that phase angle is going to be minus 90 degrees. That's kind of nice. And just like this, look, when you write like right here, if I write negative 2, I always write the operator first and then the magnitude. That's not a negative 2, that's a positive 2. I always write the operator first and then the magnitude, right? My point here, positive 2 means 2 with a phase of, I'm pointing to the wrong thing because I'm getting excited. This 2 right here, that 2 right there is positive 2, and that means 2 at a phase of 0 degrees. Or this 2 over here is 2 at an angle of 180 degrees. So I can write it like that. The point is, I always write the operator first. So here, when I want to write this operator, I want to write the operator first and then the magnitude. Or here, I'm going to write minus I3. 3, I want to write the operator first and then the magnitude, just like I do when I use these operators. But we got one problem. Anybody see the problem? It's a real simple problem. What's wrong with using an I? What's wrong with using that in electrical engineering to represent the operator for phase, angle, 90 or minus 90? Why wouldn't I want to use an I?
I sometimes is used for current.
Yeah, right. Electrical engineers already use that. The math people don't care about current. They can use I if they want to, but the engineering people, we care. We care because we already use that. Sorry about your luck, math person, but we can't use I. You can use I in math. In electrical engineering, I'm going to use let's use J. We're going to use J. So instead of using the I operator, like in math, we're going to use the J operator. We're going to say if I have positive, not I, if I have a positive J, that represents a phase of 90 degrees. And if I have a negative J, that represents a phase of minus 90 degrees. So now I can get real numbers. And God was like, funny. God made it so, or whatever you think things came from. Well, I'm not trying to push God or anything, but I'm just saying it was kind of weird. God gave us things that happen not at 0 or 180, but at 90 and minus 90. I mean, you got to admit, that's kind of weird, but it happens. So we got to have ways of representing those numbers. So now I can write real numbers, and you'll know what I'm talking about. I can say, look, I got +5, that's a real number. I got -7, that's a real number. The phase here is 0. The phase here is 180. I can write minus J 120. That's a phasor that's 120 units long. But the phase is 180 degrees. I can write 15, put a positive J in front of it. That's a phasor that's 15 units long. It has a phase of 0 degrees. Now we can talk, a phase of 90 degrees and minus 90. So now we can talk about imaginary numbers. You'll know right off by just looking at the phase. I'm dealing with if it has a J in front of it, it's an imaginary number. If it has a plus sign or a minus sign, it has then at that point it is a real number. Now, and I don't even know if I want to go into it. Let me. I probably should not even have this on the topic sheet, but I found this to be interesting. Let me show you this. You hear right here on the topic sheet. It says that J is a rotational operator. J is a rotational operator. I'm going to show you what I mean by that. That has absolutely no application in this class. None whatsoever. It's just a nice little math trick. So I'll show you that, but other than that, don't worry about C. So this is interesting because now, look at this. Let's clean this up and let's talk. So what I've said so far is the starting point and what you already know about, even though I asked you not to act like you didn't know anything, is we started with real numbers and the real number line. Got negative numbers this way, and positive numbers that way, and on that real number line, we talked about the idea of phase and that plus and minus sign actually indicates a magnitude of a certain amount with a certain phase. Phase being either 0 degrees or 180, depending on if I'm talking about this or that sign. Then, because we have these quantities, now you don't know what they are yet, but you will. We have these quantities that don't happen at 0 degrees. They don't happen at 180 degrees. There's certain quantities in AC that only happen at 90 degrees or negative 90. I can't deal with those on this number line. So the math people come in and say, well, engineer, I got another. We have imaginary numbers. We got numbers that have phases of minus 90 and plus 90. So we can do this. We have this other axis called the imaginary axis. And even though we call it the I-axis, since you already use I for current, you're going to call this the J-axis. This is the plus J axis, and this is the minus J axis. And so if I give you a value like -3, that's a real number. +3, that's a real number. Minus J15, that's the imaginary number, plus J20, that's the imaginary number. So now depending on where my points are, I can plot points here, give you real numbers, and I can plot points here and give you imaginary numbers, and you know what I mean now because you got the phase for each one of these. But guess what? If I have a line, it's just a line. But two lines, if you had your geometry, two lines define a what? Two lines define a what?
A plane.
A plane. I was going to give you a hint and say, I was telling my DC class, we were talking about action at a distance forces, and we talked about gravity and magnetism, and gravity, magnetism, and charge. And I said, all these action at a distance forces have something in common. It begins with the F. And I heard crickets. Nobody said anything. I even played hangman with them. It wasn't until I said, you play baseball on it, and somebody said, a field. They all have fields. Yes. All right. So I forgot what I was going to tell you now. I went off on my tangent to tell you about the other story.
Plane.
Plane. I was going to tell you can fly in it, but that kind of plane, is it spelled differently? It might be spelled different. I don't know.
I think we need an axe.
We need what?
Axe.
X.
Yes.
What do you need an X for? Is that Michael?
Yes.
Michael, you're causing trouble for me. What do you mean we need an X?
X in,
Are you saying this?
Mm.
Which way?
yeah, in the middle of the line, yeah.
Here?
Yes.
Okay, I don't even know. Okay, all right. Let me keep going because, God, it's 5:07. We're past break time. Let me keep going, and Michael, I don't know. Two lines define a plane. Two lines define a plane. Not only that, think about this. If we stay on this axis, all my values, either plus or minus, all of them are real values. If I stay on this axis, all my values are imaginary values, either positive or negative. But there's no reason why I couldn't come off into like a point, since I'm dealing with a plane. What if I come right here to that point right there? Now it's not a real number, and it's not an imaginary number. What is it? Now I actually have a number that's kind of a hybrid. It has two parts to it. Part of this number, let's say this value right here is A, and this value right here is JB. So this number right here, let's just call this number right here C. That number C is not strictly a real number. It's not strictly an imaginary number. It's kind of like a dog, a mixed breed. I like that. It's like a mixed breed. It has a real part and an imaginary part. Matter of fact, if I want to get to C, I can say go over A units. And in this case, go up JB units. Well, daggone it. So I got this weird looking number. It has a real part and an imaginary part. It has all these pieces. That's kind of complex. What could we call that? Let's call this a complex number. Let's call the complex number, and then what I would mean is a complex number, by definition, a complex number is a number that contains a real part and an imaginary part. So let's use that as the definition of a complex number. So now I got three kind of numbers I can talk about for this class. God, we're like, this is kind of arrogant. We got to have our own numbers for our own. Yeah, we need it. AC people need it. We got three kind of numbers for this class. We got real numbers. We got imaginary numbers. We got real numbers because the world works on real numbers. We got imaginary numbers because God or somebody gave us these funny quantities in AC that don't happen at 0 degrees or 180. These quantities happen at 90 or negative 90. And every once in a while, I have something that's not even on the axis. It happens out here or here or here or here. What kind of number is that? Well, I don't know, but I do know that that number has a real part and that number has an imaginary part. So to get to it, I got to go over a certain amount on the real axis and up or down on the imaginary axis. We're going to call it a complex number. So by definition in this class, a complex number is a number that contains a real part and an imaginary part. A complex number is a number that contains a real part and an imaginary part. If you're sitting at home right now wondering, why are we even talking about this stuff? The reason we're talking about this stuff is because next week, when I come in here next week, I'm going to change all these words like real axis, imaginary axis, and complex number. I'm going to take away the math meaning and write in the engineering meaning. And if you know what I'm doing right now, when I do it, you're going to be like, man, I get that. That is so crystal clear, it's ridiculous. So just follow me now, and next week this will make sense when I introduce AC oppositions to you. So, questions or comments on this so far? Questions or comments? Okay, well, I want to give you a break because my mouth, I keep talking and drinking this. You probably think that's water, don't you? I shouldn't say that. I want to take a break, but this is not a good place for me to stop. I want to finish this, and then we'll take a break for a few minutes. You can go do whatever it is you do when we're not on camera. We'll come back, but I want to talk about a couple more things here. I mentioned that the J operator is a rotational operator. And what do I mean by that? It's really it's a math thing. It has nothing to do with electrical engineering. But just to show you what I'm talking about. Why do we need I? Anybody know why? What is the meaning of this in math? What is that? I mean, it stands for imaginary number, but what is it for?
Square root of -1.
Yep. Let me show you. Who is that? Who said that?
Jacob.
Jacob, you're smart. Jacob is really smart. He always answers the hard questions. Michael, you just muffle your microphone, so I don't know what you're saying, so that way you're always right. And you guys got to start laughing at my jokes as I'm going to stop telling them. I spend a lot of time coming up with these jokes. Only be wasted on crickets because you don't laugh, you don't turn your cameras on. I can't even see if you're smiling at my jokes or nothing. And you pay for these jokes, guys. You pay for a lot. You pay in your tuition. There's a part of your tuition that goes to my jokes. So you got to start laughing at them. So here's the thing. You can take the square root of like 9, right? You can take the square root of 9, and you know that's 3. And so we like to be able to take the square root of -9, but the problem is you can't do that. You can't take the square root of a negative number. It's like a math law. You get a math ticket if you try to break that law. That's funny. I like that joke. I just made it up, by the way. So how would you handle this? I want to be able to do the same thing here that I did here. And I don't know who came up with it, but somebody said, well, you know what we could do? Let's just hide this -1. What if we hide it? What if, since I know that if I have the square root of AB, since I know that that's equal to the square root of A times the square root of B, let's use this in reverse to solve this problem. What if we write this like that? What if I say that this right here is the square root of 9 times -1? So that right there is like the A, and that right there is like the B. Well, if that's the case, then if I go from this to this, then I can say the square root of 9 times the square root of -1, that's the same as the square root of this. And so I was like, all right, well, that's kind of cool because I know what this is. That's just this. So I know that gives me a 3. But I got the same problem here that I had over here. I still got that square root. I can't get rid of it. And somebody said, let's just hide it. Let's hide it in this. Let's hide that in that. So we're going to say, all right, I equals, and then I can just write this as 3i. If I go with the idea of when I write a positive 3, I write the operator first. When I go with a negative 3, I write the operator first. When I do a j, I do a j3. Or minus j, I do a minus j4. I write the operator and then the magnitude. Then you probably want to write the operator first and then the magnitude. And they just hit it. Well, you talk about sweeping the dirt under the carpet. That's all the math people did. They just swept it. But we work with that. We work with that. So
can you change the color, please? I cannot see.
Sure.
Yes.
Change my color.
Writing color. I just changed.
Oh, the
your pen.
marker color.
Yeah, your pen. I cannot see on that.
Okay. I was just being funny, but I forgot you guys are not laughing, so I'm not going to waste any more jokes on you all. I'm going to go home, tell my mom this is the most unresponsive. Okay, so what I wrote, was that Michael?
Yes, yes.
But the black is okay here, I'm guessing.
Black, yeah, black is okay. Just
All right,
your
so-
color. Just give it to Becky to your mom. Maybe she need it.
Okay, so we say I is going to equal the square root of -1. So if I take I and I square it, that's like taking -1 and squaring it. If I square something that's being squared, what do I get? I get -1. So if I take I squared and I square it, I undo the square root and I get -1. So it works the same way with the J operator. Since instead of I, we're using J. So that J is really equal to the square root of -1, and J squared would equal -1. Just the way to think about it. Now, why am I doing this? Why am I wasting time? I don't even know why I'm doing this. No application of what we want to do in circuits. It's a math thing. I've seen it in a book somewhere. It says that the J operator is a rotational operator in this sense. If I have the axis, the imaginary axis and the real axis, if I have this, and I write the operators all around it, like this is plus, and that's a plus J, and this is a minus, and that's a minus J. And then what they say is that phasor, as that phasor rotates around, it points to, from here, it goes 90 degrees, you go to J, to minus J, as it goes around 360 degrees. Every time it moves around a quarter of the way, it's a product of J. Every time it moves around a quarter of the circle, it's a product of J. So what I'm saying is, if I start the phasor here, oh, you said you can't see I think you can see the green. And I go around, so this is right here, this would be a product of J, and this product would be J times J, and this would be J times J times J, and this would be J times J times J times J. So every time you rotate the phasor around, that quarter of a rotation is equal to a product of J, or a factor of J. I'm using the word the wrong way. So this is J, and this is J times J, and this is J times J times J, and this is J times J times J times J. Every quarter represents a factor of J. And again, we're not using this for anything, but it's just kind of neat if you think about the fact that since I or J is equal to the square root of -1, if I take this and square it, and I take this and square it, I get J squared equals -1. So then that means that I start here at 0, and I go right here, that's a J. I come over here, that's a J times a J, but a J squared is a -1, and that's what that represents. If I go down here, that's a J times a J times a J. Well, this part right here is a J squared times J, but J squared is -1, so that's really just a minus J, which is what it is right here. And over here, it's a J times a J times a J times a J, so this is J squared, and this is J squared. But J squared is -1, and that J squared is -1, and -1 times a -1 gives me a positive, so I get that operator there. Now, if you didn't understand that, Don't even worry about it. If you understand it, cool. You're never going to use it. I just thought it was interesting. I don't even know what book I saw it in, probably 20 years ago. Thought it was interesting. Now, this is a good point, a place for us to stop. So it's like 20 after 7. Let's take a break. I don't want a long break. Let's just take a 5-minute break. You got to leave the camera for a minute. I'll come back. It's 7:20. I'll come back a little after 7:25, and we'll pick up where we left off. So let's take a break now for 5 or 6 minutes, and then we'll come back, and then we will do some more of this stuff. All right, we're going to start up in 1 minute, 60 seconds. Okay, so hopefully you guys had a nice break for a couple minutes. So, we talked about the complex plane. The complex plane consists of a real number axis and the imaginary number axis. We have these operators that I use. I use a plus operator to represent a phase, 0 degrees, negative operator, phase of 180, plus J to represent a phase of 90, and the minus J to represent a phase of negative 90. And then I said if a number is on the real axis, it's a real number. If a number is on the imaginary axis, it's an imaginary number. But what about if I have a number in one of the quadrants? Like what if I have a number right here? Well, that number would then have two components to it. It would have a real component. So let's say this right here, that's the real number A. It would have a real component, and then this number here, let's say that's the imaginary number, JB. So to get to this point, we can call that point C. That's point C. C would equal, I would go over A units and go up plus JB units. And then this number has a real part, that's the real part. And it has an imaginary part, that's the imaginary part. And a number that has a real part and an imaginary part is called a complex number. So there's two ways to define the term complex numbers for me in this class. You can define a complex number as a number that has a real part and an imaginary part, or you can define a complex number as a point in the complex plane. Either definition is okay. A point in the complex plane. So on the topic sheet, it says we're going to talk about why do we use complex numbers in AC? Well, the answer is that just real numbers by themselves won't work. And in reality, just imaginary numbers by themselves won't work. Because in AC, we have numbers that are real. In AC, we have numbers that are strictly imaginary. And then in AC, we have other quantities that are part real and part imaginary. So it turns out to do any kind of math in this class, we got to deal with real numbers, we got to deal with imaginary numbers, and we got to deal with the mixed breed of the two. We got to deal with complex numbers. So we need complex numbers in this class. What is a complex number? Well, we said a complex number consists of a number with the real component and an imaginary component. That's one way to define it. Or you can define a complex number as a point in the complex plane, but then you got to say the complex plane consists of two axes, a real axis and an imaginary axis defines the complex plane. So that puts us on the topic sheet at C and or E and F. E, rectangular form, F, polar form. I skipped over D, it says J is a rotational operator. I showed you that, but it's no big deal. But you see right here, to express this number, this tells me how many units to the left or to the right to go on the real axis. And this tells me how many units up or down to go on the imaginary axis. And when you do that, if you start at the origin, and if you go over, left or right, or up or down, you end up going over one way and up the other way. And if you draw lines like I did here, you see how that represents? It's like a rectangle or square. It's like a square, a rectangle. And so they call this form of a complex number, that number, they call this form rectangular form. That's the rectangular form of a complex number, because when you graph it out, it looks like a rectangle. The rectangular form of a complex number. So when you see a complex number, if it has a J in it, it's a rectangular form. Well, what we use in this class, we use an R to represent that form. So this R, when used the right way, it means rectangular form. I'll show you that. This means rectangular form of a complex number. Well, if it's a rectangular form, then I must be hinting at that there's another way to write this complex number. What's the other way to write it? Well, what I'm really asking is there another way to get to this point? This tells me exactly how to get to that point C. This tells me to go over A units on the real axis and go up positive JB units on the imaginary axis, and I can get to that point. It's over and up. Is there another way to get to it? And the answer is yes. If I do this, imagine I have a, let me see, I need another color. I guess I'll try this purple. Now, I don't know if you guys know, we used to call them a compass. I don't know what you guys call them, but it used to look like it was like a metal thing in school when we were kids. It's like a metal thing like this. And you can open it like this, open it and close it. It was metal, it had a point right here. And right here, you can put like a pencil there, and you can put that point on paper, and you can draw circles with it. You guys know what I'm talking about? You can just say yes.
Yeah.
Okay.
Yep.
Yep. I said yes. I got a yeah, a yep.
Yes.
Thank you. God, you guys are supposed to be college educated, talking about something. Yep. Okay, I'm just joking. So what you could do if you had that thing, you could come up here and you can figure out how far that is away from the origin. And then you can take that and draw a circle. So basically what you would do with that thing is you would draw a circle right through that point, like that. And then what you could do to get to that point, you could have that radius vector. Remember that phasor, the radius vector? You can put that there and just extend it out to the end of the circle. So if I start here and extend it all the way out here, then that would be the radius of that circle. So I can have, if I have the radius of the circle, and then once I get the radius of the circle, you tell me how far up or down to move that radius to get to that point. So I can start here, get the radius of the circle, and I say, all right, go up so many degrees. And I can go up so many degrees to get to this point right here. So that would be like the length R. I gotta know R, and then I gotta know how far up or down to move it. We'll just call that theta. So another way to get to this point C, another way to do that, instead of going over A units and up JB units, I can use a radius vector idea and go out a certain radius and then go up or down a certain number of degrees. And so this right here is my radius vector. And then that right there is my angle. And if I write the complex number like this, they call that the polar form. The polar form of a complex number. Okay, well, let's clean this up. So what I'm saying is, if I go over and up or over and down, I can say to get to C, I go over A units and up or down B units. Or I can say to get to C, I go out so far on my radius vector, and I go up or down so many degrees. And if you do it like this, that's called rectangular form. If you do it like this, that has the name polar form. And to represent rectangular form, I use a capital R, and to represent polar form, I use a capital P. And don't confuse this R with that R. This R was the radius vector. So I got two different ways to represent a complex number. You might say to yourself, well, why do we need that? Why do I need two different ways? Will actually be clear here tonight. You'll see why we need both ways. All right. So it'd be nice to be able to, given this, go to this, or given this, go to that. It would be nice to be able to convert from one to the other. And that's where this R and the P come in. Part of a operator, I want to, I can say I'm going to multiply, take the square root, I can divide. I got these operators that show what I'm going to do mathematically. We also have an operator that says I'm going to start with this and go to that, or I want to start with this and go to that. So in this class, this is going to represent a conversion. This is going to represent a conversion from polar form to rectangular form, and this is going to represent a conversion from rectangular form to polar form. So let's look at that. Let me clean this up. And let's say I'm given this. I'm given that. I'm given a complex number in rectangular form. So I plot it. I plot that. Here's my complex number. If I plot it, this would be A, and that would be JB. I'll plot that. So given this and this, how do I find the radius vector in theta? Now, I'm going to write that in blue. The radius vector starts here and comes up to there. So given this number right here and this number right here, how could I come up with this number right here and this number right there? Well, since I have a point there and I drop the perpendicular down, what do I have right here? What is that? We would all recognize that as a right angle. And that's nice because we know all about right angles, and I know you know about right angles because you can't take trig, at least you're not supposed to come in this class if you don't know trig. So you know all about right angle triangles. So if I know that this side right here and this side are the same, I know that this has a quantity of B units tall, and this is A units long. So I know the two sides of this right triangle, and what I want to know is I want to know the hypotenuse. I'll put it in blue. What I want to know is this and that. How do I figure that out? Well, this long side right here, R, of course, you know that's called the hypotenuse. So how would I calculate, given A and B, which are called legs, the legs of the triangle, given A and B, how would I find R? How would I find the hypotenuse?
Pythagorean theorem.
Pythagorean theorem. You know, Pythagoras says that if I take the legs and square them, the sum of the legs equal the sum of the hypotenuse squared. So I can say that R squared is equal to A squared plus B squared. And since I want to know R, I'm going to take the square root of this side and the square root of this side, and that'll tell me half of what I want to know. That gives me R. So all I got to do is take these two, and I can say R is going to equal the square root of A squared and B squared. So So that gives me this part of it. How do I get this part of it? What do I do? Well, if you remember, what we know is this side and this side. So we can use one of those trig functions that you learned about. Let's see, there was the sine, cosine, there was a tangent, cotangent. See, well, the other three we don't need because you can do everything with the sine, cosine, and tangent. So let's see. This is a side opposite the angle. That's the opposite side. And this is the side adjacent to the angle. That's the adjacent side. And that's the angle. So the sine function, the trig function I need is one that's going to deal with the opposite side and the adjacent side. And you might remember, that's the tangent. Without going through all of them, that's the tangent. Tangent of theta, the tangent of theta is equal to the opposite side over the adjacent side. So that's what we can do. We can use that. The opposite side is b, so the tangent of theta is going to equal b over the adjacent side, which is a. So that's the equation we can use to solve for that theta. So we know b over a, but I want to know theta. So how do I undo a tangent? Well, the way you undo a tangent is you take, in the old days they called it the arc tangent. Now they call it the inverse tangent. So given this, I can get this ratio here. But given the ratio, I can find the angle by just doing the inverse tangent. So theta would equal the inverse tangent or arc tangent of b over a. And so I can use that. Theta equals inverse tangent of b over a. And this right here will give me from rectangular form to polar. Two simple calculations. So you want to write these formulas down. Of course, if you guys did lab 1, then you already know how to do everything I'm showing you. This is like old news if you did lab 1. If you didn't do lab 1, you're going to try to do all of those calculations before next Tuesday, you're going to be in trouble. It's a lot. You had like 3 weeks to do it, so you should have did it. Okay? All right, I get that. Given the size of the triangle, it's easy for me to get the hypotenuse by using Pythagorean theorem and the angle by using the inverse trig function. I get that. I mean, it's not that bad. But what if I'm giving it the other way? What if I'm given r and theta and I want to figure out a and b? How do I do that? Well, again, we go back to the triangle. All this stuff is trig stuff. The nice thing is this right triangle trig. Right triangle trig is easy. So, given a right triangle, and I know this angle right here, I know theta, and I know r, how would I figure out this over here, which we call that b, and this over here, which we call that a? If I can figure out that, and I'm going from polar form to rectangular, I'm doing the opposite of this. And if you think about it, it's actually pretty simple because it deals with, here you know a side and an angle. If I know a side and an angle, then I'm going to use one of those trigonometric functions, it's hard to say when you're tired, to solve the right triangle. And so let's see if we can list them out. The sine of the angle is the opposite side over the hypotenuse. Cosine of the angle is the adjacent side over the hypotenuse. And the tangent of the angle is the opposite side over the adjacent side. So that's what they taught me in math. So the question is, like, if I want to figure out A, which one would I use? Well, I know, I got to have one where I know the hypotenuse, so that wouldn't be this one. because I only know the hypotenuse in this side and this side. And A that's the side adjacent to the angle. So that would be this one. That would be this one. So I can find A by taking R cosine theta. If you want to know where I got that from, I got this right here. The adjacent side is A. The part I know, the hypotenuse, is R. And the other part I know is the angle, which is theta. What I don't know is the A. And the way I get the A is I multiply both sides of this by R, multiply this side by R and this side by R. That'll cancel out, and I got basically A equals this. A is B, A is not, this should be R. A is R cosine theta, because I'm using the R here. And using the same logic without going through any derivations, B is going to be R sine theta. So going from one form to another is real easy if you know this, Pythagoras, or if you know this, just from the trigonometry, and going from one to the other is pretty simple. So, there you go. Anybody have any questions over that? It's a lot of talking and trig stuff, but hopefully follow the math. And if not, when we do a problem, you probably will. Questions or comments? Okay, well, I got one more thing I want to show you here, and then I want to do some practice problems. And what I want to show you actually is a problem with this right here. So let me clean this up, and I'm going to show you the problem and how to correct it. So make sure you got these down. Again, if you did the lab one, this should be old news to you. You've done all this stuff in lab one. But some of you might not have did lab one. Or maybe this will help emphasize some things in lab one when you see somebody else talking about it. Let me show you the problem I was going to talk about. The issue is this. When you're given a complex number in rectangular form, in polar form, C equals R at some angle. Now, I don't know, I'm sure somebody out there have you dealt with vectors before. I think I asked that question on the first day, what's a vector? But if you didn't, it's okay, it's pretty simple. But for those who know vectors, if I tell you that this right here is, if I tell you that that vector represents vector A, if that vector represents vector A, how would I draw this vector? If this is A, how would I draw negative A? Where would that be?
Well, you would move the arrows.
Change this direction, the arrow.
Okay. Well, if A is here, then negative A is right here. If that's A, then negative A is over here. It's always the mirror image. I don't know if you know what I mean by mirror image. If I put a mirror right here, it's the image you will see in the mirror. So all I gotta do is flip the vector the other way to get the negative of it. Now, why am I showing you that? Well, it turns out that when you have a number like this, is it proper? Let's say I have a negative complex number. So if I have a negative complex number, then what I'm saying is, what I have is I got a minus R angle theta. And this is actually improper to write it that way. You're not allowed to write the magnitude as a minus magnitude. And the reason is, think about how we got this polar form. The way we got the polar form is, we had a number here that was a complex number. And I said what we're going to do is we're going to draw the arc of a circle. So we put a circle out like that, and then we got to know the radius of that circle. So we do the radius out like this, And that's where that r came from. The r is the radius vector. Basically, it's just the radius of that circle. And it turns out in math, you can't have a negative radius. What would that look like? You cannot have a circle with a negative radius. I don't even know how to draw a circle with a negative radius. So radius is always a positive number. So given this number right here, how would you write it not as a negative number? So let's change this from C. Let's say that this point right here represents this number. That's that point. And I don't want to write it as a negative. So what could I do? I don't want to write it as a negative.
So it's theta plus or minus 180?
Exactly. So here's what she's saying. Hopefully this makes sense. And actually, well, I guess it doesn't matter. So if I take my radius vector, if I take this, and she said it's going to be theta plus or minus 180. Now, why plus or minus 180? See, I can get rid of the minus sign if I add plus or minus 180 to the vector, right? Because if this right here represents this point, right? That negative r represents this point, and this r, let me get rid of this because this is confusing. Now just follow me here. This will make sense to you. If this is negative r, this right here, this represents negative r. That's negative r. And r is over here. If that's negative r, then this is r. You guys agree with that? Because that's the mirror image. So what I can do is take r, I can take this, and I can add or subtract 180 degrees to it. And that, depending on whether I'm adding or subtracting the 180, I'm either moving it this way or this way. That's the plus or minus. It doesn't matter if you add or subtract. What you're doing is you're shifting that radius vector around to point at that point. And so what I'm doing is I'm getting rid of the negative sign in front of the r. I'm using that 180 to get around to where I want to be. Now, I don't know that I will follow what I just said because it sounds confusing, but here's what you got to remember. That if I want to get rid of the negative sign, all I got to do is erase it and add or subtract 180 from the phase angle. That's all you got to remember. That's what that formula is saying. So I'm trying to explain why. I don't know if I'm doing a good job or not, but if you understand why, fine. If not, this is not math. I don't really care why. I just want to know how to use the equation. So having said that, guys, take a minute, get some pen and paper and your calculator, get all that out. And I want to do some practice problems. So I'm going to pause for a second. Get your calculator out. Get your pen out, your paper out. And we're going to do some calculations here. I'm going to wait a minute. I'm trying to see what we can do. Determine the quadrant. Okay, so we get to 3. Okay, so let me share the document in case you don't have it. I want to do problem number 1 and 2, and number 3 I gotta talk about number 3 before you do it. But I'll share the document in case you don't have it, and I want you to do take a minute, do problems number 1 and 2. So here is the document. At the bottom are practice problems, and I want you to do problem number 1 and problem number 2. So I'm going to give you a few minutes to work those. We'll come back, we'll do them on the board. I want to talk to you about problem number 3, and then we'll do problem number 3. So I'll be off camera for a minute. I'm gonna leave this here. You work those out for me, and I'll give you maybe 5 minutes to work these, and we'll come back and talk about them. Problem number 1 and 2. Give you about 1 more minute, and then I want to take a look at these problems. Okay, so if you understood the direction, these are actually pretty simple. Number one, it says determine the quadrant for each point and sketch the complex number as a point and as a radius vector. Just to remind you, when you have your axis, you name these quadrants. So this would be quadrant 1, this is quadrant 2, 3, 4. You go in the counterclockwise direction, 1, 2, 3, 4. And what you don't do is what I do here. You don't use you use the Roman numerals here. So this actually is quadrant number 1, quadrant number 2, quadrant number 3, quadrant number 4. So you do it like that. So you might remember that you can easily tell if this were X and Y, then X here would be this one. X is positive, Y is positive. And over here, X would be negative, Y is positive. Down here, they're both negative. And over here, X is positive, Y is negative. Well, we don't have X's and Y's. We're using A and B. So I can just look at, if the first number is A and the second number is B, I can just look at the sign and tell which quadrant I'm in. So if you don't remember that from trig, it's pretty simple. So this one, they want me to draw this. I got it, since they're both positive, I know I'm in quadrant 1. So it says draw it as a dot and a radius vector. I just kind of got it. You don't have to get it and measure it with a protractor and ruler and all that. Just kind of guess where the point is. Over 3 and up 4 is probably like, something like that. So I'll draw it like that. And then there's my radius vector and there's my complex number. So that's all you got to do. Just get used to thinking about which quadrant this is in. And this has an A value of 0, which means that this radius vector is going to be on the axis and it's pointing down this way. So the point is down here, pointing like that. And that would be my minus J6 down there. So that's not on the quadrant, it's actually on the axis. If I have a 0 here, then I'm on the axis. Or if I have a 0 here, then I'm on the axis. Right here is where both quadrants are negative. That's this quadrant. So it'll be over here in the third quadrant. So I might draw over 10 down 20. I don't know, it might be something like that. So really all you're doing here is just putting the quadrant in the arrow in the right quadrant. Make you think about this stuff you learned in trig. So again, hopefully you found that to be pretty simple. And then they want you to do, yep, go ahead.
Draw again that one, you have that in green color. It's not clear.
This?
Yes.
Yep. Let me see if I got a darker marker. Let's see if this brown works. Oh, that's terrible right there. My black, I use it all the time, so I use the ink in this up faster than anything. I'm just running out of black markers. So this is A, B, this is plus, plus, minus, plus, minus, minus, plus, minus. So I'm just looking at these signs, minus, 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 minus means it's down here. On this one I had, or this one I had plus, 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 plus would be here. Now down here, same old thing, but instead of giving us the complex number in rectangular form, they gave it to us in polar form. Big deal. You just kind of got to know your angles. So you got to know as you go around the circle, we always start here, we go counterclockwise. Counterclockwise. Sometimes they call it anti-clockwise. But you got to know that 0 degrees is here. I guess you might not be able to see this. 0 degrees is here. 90 degrees is here. And as you go around, 180 is here. 270 is here, and so forth. So this is 5, our vector is 5 units long at an angle 30 degrees. So in between here is like 45. So 30 is probably like somewhere like right there. So I guess I should draw it over here. So just kind of, you don't have to have a protractor and actually be exact with this. Just know that, well, 30 degrees is like, it's kind of right in here somewhere. So maybe that's C. That's my point. So just kind of guess where it is. Here, now what's this negative thing? Well, when you measure an angle, typically you measure the angle like this. You go from here and you go in a counterclockwise direction. If you do, you report the angle as a positive number. You can also measure this way and report it as a negative. So that's what they did here. They said, all right, I got my vector, and I'm going to start here, and instead of going this way, I'm going this way, minus 120 degrees. So if I go this way, that's minus 90. This is minus 180. 120, negative 120 is somewhere between these two. It's probably 90 and a couple, so it's probably like right in here somewhere. And then my angle right here is this one. That's the theta equals minus 120 degrees. Uh-oh, what about this one? What's going on with that? What's the problem with that one?
It's a negative R.
I can't have a negative R. You're not allowed. You're not allowed to have a negative R. So what am I going to do with that? Well, we can erase that if we do what?
Plus or minus 180.
Yep. I can get rid of this. If I add or subtract 180 to this, I'm going to just add 180. Probably better to subtract 180 because then you get a smaller angle, but I don't really care how you do it. As long as you know, I can erase that. If I add, let's subtract 180. It'll give us a better angle. So 60, 70, is that 120? It's going to be C equals pop. Again, I don't know if you can see this. I'm only going to be stuck with one color because all my markers are dead. And Michael, you can't see anything other than the black one. I got to go buy some more markers. This is going to be 4.2 at an angle of 678. So that's minus 120. So I can write it like that, which means that I'm over here, like in the third quadrant. So this one's like over here. So that's an example of how you get rid of that negative sign. So this is all pretty easy if you've probably seen this before in your trig class, I'm sure. At least I learned it because I took this stuff back in the 90s, so you probably weren't even born back in the 90s. Ooh, that's a lot. Anybody have any questions or comments? Okay, well, we got more practice problems to do, but I got to show you something. There's a little problem with your calculator. So get your calculator out. I want to show you there's an issue with it. There's an issue with your calculator. I want to point it out and tell you what you need to do to correct it. So get your calculator, and then while you're doing that, I'm going to clean the board off. And I want to make sure you understand what I'm getting at here. If not, you're gonna be faced with some mistakes in the class. I don't want you to have the mistake. Give you about 30 more seconds to get your calculator out. I stopped drinking these Diet Cokes a while back because I was addicted to them. And I've been here teaching at night with you guys, and I'm getting back on I'm gonna have to go to Cokes Anonymous. There's an Alcoholic Anonymous. I'm gonna go to Coke Anonymous. I'm a Cokeaholic, and I admit it. All right, let me show you the problem with your calculator. So, you know that when I have a coordinate system, that the sign here is positive, positive. So if I have A and B, that's A, that's B. So that's positive, positive. This would be A negative, B positive. They're both negative. And here, A positive, B negative. So we just looked at this, so you know that. So Remember where when I'm converting from rectangle to polar, when I'm going from rectangle to polar, what I got to do is I got to find r and I got to find theta, because polar is written as r at some angle theta, right? That's polar. Well, to find r, that's easy, because all I got to do is take a and square it, plus b and square it, and take the square root of it. So that's easy, no problem there. The problem is when I find theta. See, when I find theta, what I got to do is I got to use the inverse tangent of b over a. These are the equations that we derived last hour. So we got to use it, and the problem is right here with this. So what happens is, let's say, let's say my complex number is right here. So it's in this quadrant. So that's my complex number. When I go to do this, what I'm doing is, I'm going to trying to get a marker that's different color, but that Mike can see. I think you can see that purple. Okay, so when I'm doing this is where the problem comes up. When I'm doing this, if my complex number is in quadrant 1, then what's going to happen is, I'm going to say, all right, theta is equal to the inverse tangent of b, but b is positive, divided by a, but a is positive, right? Well, a positive divided by a positive that's just going to be the inverse tangent when I divide this of a positive number. Everybody agree with that? So when I'm right here, this is how I'm going to get that number. Well, the problem is this. I get the same thing over here. If instead of being in quadrant 1, let's see, my complex number was actually down here in quadrant 3. I know it's in quadrant 3 because I got a minus sign right here and a minus sign right there. So I know that's in quadrant 3. I know that's where it is. When I go to take that number and put in this equation, I'm going to say, all right, the inverse tangent of, well, let's see, I got b is negative, divided by a is negative. I got a negative divided by a negative, that's going to give me the inverse tangent of a positive number. Because a negative divided by a negative is a positive, and a positive divided by a positive is a positive. So if you do that in the calculator, if you take a number over here where they're both negative, and you do this inverse tangent thing, if you're here, it's going to give you an angle right here. Does everybody see why I'm saying that? So I got a problem. I'm cool if I'm right here. I'm just going to get, your calculator will give me the right answer right here. It will give me the correct answer in quadrant 1. If I'm in quadrant 3, it's going to give me a quadrant 1 angle because a minus divided by minus is a plus, just like up here. So this is a problem right here. This is a problem. Okay. But what about this one? What if my number's over here? Well, let's check that out. If my number's over there, then I'm going to have, let's see, theta is the inverse tangent of b. Well, b is negative. Divide a. Well, a is positive. Well, a negative divided by a positive, that's a negative. So really, that's the inverse tangent of a negative number. Okay, I'll get that. So I'll get it right here. That's cool. My calculator will work. But the problem is, what if it's not here? What if my number is actually over here? And I put these numbers in. It's going to give me an angle over here. If I have an angle in the second quadrant, the calculator is going to give you an angle in quadrant 4 because of this. Because if I'm over here, then this equation is going to look like this. Theta is the inverse tangent of, let's see, b, but b is positive, a, but a is negative. It's going to be the inverse tangent of positive over negative. Well, positive divided by a negative, oh, that's a negative. just like up here. So the problem is that if I divide this way, I get a negative, or this way, I get a negative. So this, when I do it, it's going to give me the same answer as that. So even though I know I'm over here, it's going to give me an angle over here. So this is a problem. It's going to be an issue. So how do I handle that? Well, here's what you do. You got to understand that when you're doing this trig stuff in this class, and we're working with complex numbers, if I'm in quadrant 1 or quadrant 4, then the angle your calculator gives you is correct. I'll say it again. If I'm in quadrant 1 or 4, then the number you get on your calculator when you work with the tangent is correct. But if I'm in quadrant 2 or 3, it's going to give you a number that's incorrect. If I'm in quadrant 3, it's going to give you a quadrant 1 answer. If I'm in quadrant 2, it's going to give you a quadrant 4 answer. So how do you fix that? It's really okay, because here's what's going to happen. If you're in quadrant 3, then your calculator is going to give you an angle here. It's going to give you the positive angle. You know you're really over here. So all you got to do is take the angle your calculator gives you and add how much? You add 180 to it and you got it. The same goes for here. If you're over here, your calculator is going to give you as if your phasor is down here. You know you're here because your signs are negative positive, but it's going to give you an answer over here. You'll realize you're in this quadrant. You're going to take this number and add 180 to it. So let me just summarize that in case you don't understand. If you're doing a tangent, you got to make sure you're in degrees now, not radius, degrees. If you're doing a calculation with tangent, if your phasor is in quadrant, if your complex number is in quadrant 1 or quadrant 4 and you work with tangent, you're okay. It's going to give you the correct answer for the angle. If you're in quadrant 2 or 3, you got to add 180 to whatever it gives you for the angle. If you remember that, you'll be okay. Now, having said that, let's go back to the topic sheet and let's look at this now. Because on the next part of the topic sheet, they want you to, for problem number 3, they want you to do some conversions. So look at problem number 3, and I want you to do A, B, C, D, and E. For the first 3, you're going from rectangular to polar, and for the last one, you're going from polar to rectangular. So go ahead and do those. I'm going to be quiet for a minute. I want to be off camera and give you a minute to work on those, and then we'll talk about them in about 5-6 minutes. So get your calculator out and go ahead and do your calculations, and then we'll look at them together. Guys, I'm gonna give you about 2 more minutes, and I want to look at these problems. So 2 minutes.
I don't think we can hear you.
Say all that over again. You know what I was talking about? I was talking about my diagram, saying that if you are quadrant 1 or 4, got a smiley face, so that means everything's good. If you're over here, the calculator will give you the wrong answer, so you got to add 180 to it when you do that inverse tangent calculation. And for the first 3 problems, we're going from rectangular to polar. So when you start this, we know we're going to use this. We got to find R. That's easy. It's just going to be a squared plus b squared square rooted. We got to find theta. That's easy. It's going to be the inverse tangent of b over a. So the formulas are easy. You just got to, when we use this, if we're over here, you got to add 180 to this. If we're here, we're cool. So you're going to look at this and say, all right, well, which quadrant am I in? I got positive, positive. I'm in quadrant 1. I'm all right. When I use this formula, I can just go ahead and calculate it. If I do that, then the length of my radius vector is going to be 3 squared plus 4 squared square rooted. That's going to be the square root of 16 plus 9 is square root of 25. It's going to be 5 units long. And the angle is going to be the inverse tangent of this B over that A. So make sure your calculator is in degrees and not radians. And then tell me give me the inverse tangent of 4 over 3. How much is that in degrees?
5313.
Okay, I'll just say 53 degrees. We'll just round it. So the angle, if I convert this using this, I get, I'll write it like this, 5 at an angle of 53 degrees, and it's some change here, decimal point. So, but you see how to do it. So I'm okay, because I'm in quadrant 1. I get the right angle, I'm in quadrant 1. Now what about this one? Where am I? I got a minus plus means I'm in quadrant 2. So my calculator is going to think I'm over here. When I know, looking at these signs, I'm actually here. It's going to give me an angle over here. So I got to take that angle and add 180 to it to put it back where it needs to be. Put that complex number back over here. So let's try that. Let's do the next one. So I will take, to get the length of my radius vector, it's going to be minus 6 squared plus 3 squared, square rooted. So I don't know, what is this one when you do to work it out? 36 plus 9 is what? 45? I can't add. I'm too tired to do it in my head. You're going to have to help me. I start my day at like 4 in the morning, and by this time, my brain cells are fried. So how much is that?
6.7.
6.7, and my angle will be the inverse tangent of 3 divided by negatives. Now you might wonder why I wrote this way, because you know when you square that, you're going to get a positive 36. But the reason I'll go ahead and write the negative sign is so I don't forget to put it in down here, because that's not a 6. If you just write, if you don't write that, you might think that this is a 6, and that's supposed to be a negative 6. So I always stick it in there just to remind myself. So that's 1/2. So what is, I need the inverse tangent of negative 0.5. How many degrees is that?
26.5.
How much?
To round it up, 27.
Is
I
it
mean,
positive or negative?
negative 27.
Okay, so we got negative 27 degrees. So negative 27 degrees, think about where that is. Negative 27 degrees is over here, but you know from looking at the numbers here that I got a minus and a plus. Minus and the plus is over here. So you got to take that and flip it around by adding 180 to it. So then you say, all right, I got to take negative 27 degrees and add to it 180 degrees. I'm sorry, I can't do this in my head, guys. I'm too tired. What's 180 minus 27? I admit defeat. You just got to tell me.
153.
So the angle is 153 degrees. So that's an example of what I'm talking about. When you're dealing with these complex numbers, you got to be careful when you're over here or over here. Whatever angle you get using this formula, add 180 to it to get the right number. Everybody see that? So that was this one. And what about this one? Is that one going to give me the right answer, the correct answer, or the wrong answer when I get the angle?
Wrong answer.
The wrong answer. It's down here. It's going to give me an angle up here because a positive divided by a positive gives me the same answer as a negative divided by a negative. So the calculator can't tell. You have to help the calculator out. You know it's over here, so add 180 to that angle to get back where you need to be. But anyway, to get the length of the radius vector, it's going to be a minus 2, and I got to square that. Got a minus 4, and I got to square that. Take the square root of it, and then to get the angle, it's going to be the inverse tangent of minus 4 over minus 2. So the inverse tangent of 2. So what do you get for R? How much is R?
$4.5.
Okay. What about this angle right here?
63.4.
63.4.
right? So we got 4.5 at an angle of, it's telling you you're over here in quadrant 1, but you know from looking at these signs right here, you're really down here. So I got to take the 63.4. I can either add 180 to it, or you probably want to subtract 180 from it to get the smaller angle. It doesn't really matter. But what is 180? What is 63.4 minus 180? How much is that?
116.6.
116.6?
Yep.
Okay, now, if you're wondering why you can add or subtract, it doesn't matter. If you do 63.4 minus 180, you get this number. If you do 63.14 plus 180, you'll get 2 something, right? You'll get another number. But if you take the sine, cosine, or tangent of either one, it'll give you the same decimal value. So it doesn't matter whether you add or subtract or not. I just try to get the smaller angle just because it looks better. Okay, so questions over that? You see, I did that so you can see what I'm saying about quadrant 2 and 3. That's what the problem is. If you follow this, then we're okay. And then this one, we're positive, negative, quadrant 4. We're going to come back okay there. Our angle will be okay. So we'll go ahead and do that. So to get my radius factor, I got 4 squared plus minus 3 squared square rooted. And that's the same as the first one, 16. That's going to be a 5. And then when I get my angle, theta, it's going to be an inverse tangent of minus 3 over 4. How much is that?
Minus 37.
Okay. So 5 angle minus 37 is what that would be in polar form. So that's a good exercise to relate your calculator to the actual graph of where the phasor, where the complex number is, and how you have to make adjustments if you're in one of these other quadrants. So anybody have any questions over that? Well, we got one more to do. It was one of them where they gave it to you in polar form. They want you to go to rectangular form. That was, you had 10 at an angle of 45 degrees. So we're going to take this from polar form to rectangular form. So that's just using those formulas. I don't imagine anybody will have any problem with that at all. Just use the formulas. So we got to get A, which we said was R. This is like R. So it's going to be R, cosine of the angle, and then B is R, sine of the angle. So these are really simple. So I got 10 cosine 45 degrees, and this is 10 sine 45 degrees. So now I know, because 45 comes up a lot in AC, and I know the cosine, 45 degrees, it just happens to be an angle where the sine and cosine are exactly equal. And I know that the cosine of 45 is 0.707. This is going to be 7.07, and this is going to be 7.07. And again, it's just a coincidence that these are the same, because the sine and cosine, they're equal at 45 degrees. So that's the only reason why. So what you're going to do is you're going to write C equals 7.07. That's the real part, which is this one, plus J 7.07. That's the imaginary part, which is that one. So there you go. So that's pretty easy to do. And like I said, I imagine that if you have, if you did the lab, then this should be actually pretty simple. So hopefully you didn't find that to be too difficult. Now, I'm sharing the document with you, and take a look at it again. I want to take another break here in a minute, but I think I want to finish up this sheet and then take a break, and then we'll come back. We got to do that Phasor sheet tonight. I know it's getting kind of late, but we got to do the Phasor sheet. so that we're able to be in the right place for next week's lecture when you come in. So I gotta get to that sheet. But on here, they want us to do some math now. On problem number 4, they want us to, we got two complex numbers, C1 and C2, and they want us to add them. So how do you add complex numbers, and how do you subtract complex numbers? And then down here, they want you to multiply and divide these complex numbers. And then they want you to multiply down here kind of longhand. So how do you do that kind of math when you're doing complex numbers? And so let me show you what you do. It turns out that when you are working with complex numbers, it's easy to add and subtract when you're in rectangular form, and it's easy to multiply and divide when you're in polar form. So that's the reason for being able to go between the two. In the class, in AC, when you're doing calculations, your Ohm's law and all of that, sometimes you got to add, sometimes you got to subtract, sometimes you got to multiply, sometimes you got to divide, depending on what you're doing in your formula. Well, it turns out that if you're adding or subtracting, you want your complex numbers to be in rectangular form because it's easy to do that in rectangular form. Easier, I should say. And when you're multiplying and dividing, it's easier to do that in polar form. So you want to be in rectangular form for addition, subtraction, polar form for multiplication, division. That's why you got to be able to go between the two forms. Let me show you how you do it if you're going to add. If I'm going to add complex numbers, I'll just make it up. Let's say I have 2 plus J7, and I want to add to it 3 minus J1. What you got to do is make sure you have the real part over the real part and the J's over the J's. And then you just add them up like a regular number. So I'm going to start over here. I got 2 and 5. 2 and 3, my real number I get is 5. Then I got J7 minus J1, so it's going to be a positive J6. So I just make sure I have real over real, imaginary over imaginary, and just add them up. So addition is super easy. Now subtract, when you subtract, it's a little different. What we're going to do, let me show you with a regular number. If you have 7 minus 3, you know, subtract 3 from 7, you get 4, right? You know it's 4. But there's another way to do it. I can add the opposite to subtract. I can say I'm going to take 7 and add to it the negative of that. So I'm going to take 7 and add to it the negative of that. Add to the negative of that. I'll still get a 4. So I can either do direct subtraction, 7 take away 3 is 4, or I can add the opposite. 7 plus the opposite of 3 is a negative 3. 7 plus negative 3 is also 4. So I'm going to subtract these numbers not like this, but like this. I'm going to subtract by adding the opposite. So let's say I want to take this number, which is 2 plus J7. Now I'm going to subtract this number, which is 3 minus J1. So if I'm going to do that, I'm going to do it like this. I'm going to say, all right, I'm going to take 2 plus J7, and I'm going to add the opposite. I'm going to add the opposite. Well, the opposite of this, if I got a 3, the opposite is a negative 3. If I got a plus J1, a minus J1, the opposite is a plus J1. So I'm just going to flip these signs to get the negative of that. And then I'm going to add them up. Add them up. I got a 2 and a minus 3. That's just a negative 1. And over here, I got a J7 and a J1. That's a positive J8. So the difference between these two numbers is that number. So when you're adding or subtracting, it's easier to do that in rectangular form. What about when you're multiplying? You could multiply, given these two numbers. If I want to multiply, I could multiply like this. if I want to multiply these two numbers, and then what you do is like, you remember the FOIL in algebra, they taught you how to do the FOIL method? I don't do the FOIL method. I just do like this. I'm going to multiply this times that, this times that, this times that, this times that. You can do it like that. Matter of fact, the last problem on the sheet, that's what they want you to do. They want you to actually multiply it longhand like that. But it's way easier to multiply a complex number if you're in polar form or divide in polar form. Because here's all you do. Let's say you're already in polar form. Let's say you're given 3 angle of 15 degrees. You want to multiply that by, let's see, let's do 18 at an angle of, I don't want to do 18, that's too hard to remember. Let's do 10 at an angle of, I'm going to say 5 degrees. Right, so let's say you want to do that. Well, when you multiply, what you do is you multiply the angle. So you multiply the magnitudes, and then the angles, you're going to add those. You're going to add. So that's really easy to do. So we're going to multiply 3 times 10 and get 30. Look at the angle, we're going to add these. So that's going to be 20 degrees. That's really easy. So when you multiply, if you're in polar form, you just multiply the magnitude, add the angles, which means if I were dividing these, I'm going to do the opposite. Let's say I'm going to divide these instead. Let's say I'm going to take 3 at an angle of 15 degrees. I'm going to divide that by 10 at an angle of 5 degrees. So if, when I multiply the magnitudes and add the angles, it would make sense that when I'm dividing, I would divide the magnitudes and subtract the angles, and that's exactly what you do. So I'm dividing this, I would divide this part, so that's going to give me 0.3 at an angle of, now let's subtract this from that. 15 minus 5 is 10 degrees. So again, that's the reason why you want to be able to go between one and the other, is so that you can quickly do calculations like that. And there's a ton of this we do in this class. That's why the problems take so long, because you might be in one form doing Ohm's law, you got to change it over to the other form and then do the calculation in Ohm's law. So you got to be able to do really, really, really good at going from rectangular to polar and vice versa. So, having said that, let's finish up this sheet. It's about 10 till 9. I'll give you a few minutes to look at this sheet, to do the last couple problems on the sheet. Problem number 4, 5, and 6. Now, number 6, they want you to do it longhand. They don't want you to, like a lot of students, what they'll do is they'll take this and they'll convert it to rectangular. They'll take this and convert it to rectangular, and then they'll multiply it and then convert it back to polar. That's not what they want you to do. They want you to multiply just as you see it right here. So go ahead and do problem number 4, 5, and 6. I'll give you a few minutes to do it. We'll come back. We'll check it, and then we'll take a break. And once we take the break, I need to talk about what RMS is, and then I got to do the Phasor sheet. So we still got some material to go through. So we want to go ahead and get through it. So go ahead and work the problems. I'll be quiet, and we'll just go over it to make sure you understand it, and then we'll move on to the Phasors after the break. Okay, guys, I'm gonna give you about another 2 minutes, and then we'll talk about these problems.
Your sound isn't on. Or
You guys can keep a track on how tired I am by the number of mistakes I make. So you'll see as it gets later, I make more mistakes. So what I was trying to say is that they gave us these two complex numbers. They want us to add them up. They want us to subtract them using the method that I showed you a few minutes ago. I'm going to take C1 and add C2 to it. So here's C1. When I add C2 to it, all I want to do is make sure that I have the real part of the real part, imaginary part of the imaginary part, and I just add them up. So I get 5 plus J5 for that one. That's pretty simple to do. Then they say, all right, well, let's subtract them. Let's subtract these. Let's take C1, 2 plus J4, and subtract from it C2, 3 plus J1. So what I'm going to do is I'm going to do a subtraction in terms of addition. I'm going to add the opposite. I'm actually going to take this, 2 plus J4, and add the opposite of this. I'm going to add to it. That's a minus 3. This is a 3. That's a plus J1. This is a minus J1. I'm going to add the opposite. So now I got a, oh, okay. Actually, that's not right, because that wasn't a minus 3. That was a plus 3. So I'm going to switch this to a minus. I was showing that I was subtracting over here, and I confused that for a minus 3. So I'm subtracting these two. I'm subtracting this and that to make it more clear. So that's originally positive. I changed it to a minus. That's positive. I changed it to a minus. I'm going to add these up. So I'm adding these. So now I got a 2 and a negative 3, negative 1. I got a 4 and a negative 1. I get that. That's the difference between the two. So if you remember to flip the signs and add it, then you're adding the opposite and you're good to go. Does everybody see how that's done? Any questions over that one? When we multiply, I multiply.
I have a question.
Yes?
Why that sign in front of the 1? It's not a positive.
You mean right here? Is that the one you're talking about?
No, the other one. No. The way we were plus.
Your mic is breaking up.
Before the 3. It's not a minus.
This?
Yeah.
Yeah, because I'm taking, I'm doing C1 minus C2. So that is that. You see what I'm saying?
Oh, yes, I see. Oh, yeah.
I was just trying to show that you're subtracting here, and over here you're adding.
Oh, okay.
But when you do the math, that's what you come up with. So you add the opposite, and then you're good to go.
Okay.
Anybody else for questions for that stuff? All right, well, you'll find that multiplication is really easy. The ones that do C2 by C1, I got 10, angle 30, and I got 5, angle 20. I'm going to take these two and multiply them. I get 50. I'll take these two, and so I multiply these. I'm going to add these. It just so happens I get 50 again. But I multiplied these to get 50, added those to get 50, and then there you go. And then when you divide for this one, the ones that take C2, which is 10 angle 30, divided by C1, which is 5 angle 20. And for that, I'm going to divide the magnitudes. I'll get 2 angle, subtract these, 30, take away 20, 10 degrees. And on this, we're going to just flip them over and do the opposite. So I got 5 angle 20 divided by 10 angle 30. But it's the same thing. I got 5 divided by 10. 0.5, and this time I'm going to say 20 minus 30 gives me a negative 10. So multiplying, dividing, you want to do that in polar form. Adding, subtracting, you want to do that in rectangular form. Does anybody have any questions on multiplying, dividing, adding, or subtracting in either of the forms, rectangular or polar? Any questions or comments? Okay, well then we have one more to do and then we'll take a break. And this will be the last break of the evening because we should be able to finish everything up after the break. And that is number 6, where they want you to actually multiply it out longhand. You don't ever have to do that, but just to see how it's done is the reason that problem is there. To show you that if you wanted to, you could do it. So if you were actually going to do that, then what you have is this. You got two. Let me get a better marker. I'm going to have to go upstairs, guys, during the break and try to find it. Because my markers are dying on me and I feel like you can't see these. And I need another black marker. I don't know if they have any up there. So I got 2 plus J3, 6 plus J8. And I want to multiply these. Now you could, as I said before, you can convert those over the polar, multiply them, and then convert it back to rectangle. But they want you to do it longhand. So we're going to multiply this times that. It'll give me a 12. This times this. It'll give me plus J16. And then this times that plus J18. And this times that. Now, when you do this times that, you got J3, and you're multiplying that by J8. So you got to be careful because you got to multiply the two numbers. That'll give you 20, 8, yeah, that'll give you 24. And then you got to multiply these. J times J is J squared, but remember, that's equal to minus 1. So you end up with 24 times a minus 1, which is a minus 24. So make sure you see how I got that. The 3 times the 8 gave you 24, but then you got J times J, which is J squared, and as we discussed earlier, J squared is equal to minus 1. That really is a minus 24, so I got to add a minus 24 over here. And then when I add these up, and you guys might have to help me with my arithmetic. This one I can do. That is a negative 12. And then I got here, that's 20. Is that 34? I think it's minus J34. But my arithmetic is incorrect, let me know. I think that's the answer. God, these markers are really dying. Does that check what you guys got?
Yes.
I think it's, yeah.
I got plus
Okay.
34. Minus 12 plus J30, 34.
Okay. So we're good to go. So we're done. That's a lot of information. It took us, over 3 hours to do complex numbers. You're probably wondering, what the heck does this have to do with circuits? Well, you'll find that out next week. Everything will be crystal clear next week. So we have the next topic sheet. I know it's getting late, but it's actually, it'll go very quick. The Phasors sheet is, I need to talk about RMS, so take me a minute to do that. But once you learn about RMS, then the actual next sheet will go really quick. So we won't be here all night. Let's take a break, maybe 5-8 minutes, something like that. And we'll come back. I want to tell you what is RMS exactly. When we say we have an RMS value, what are we saying? We'll talk about that, and then we'll apply that knowledge to the other way to write an AC waveform, which is called phasor domain. And then we'll call it a night. So go ahead and take a break. Relax for a few minutes, and we'll come back in about 6-8 minutes, something like that. Guys, we're going to start up in about 2 more minutes. Actually, we're going to make that about 3 minutes. I got to go see if I can get some markers. I'll be right back. All right, well, I was unable to find the marker I was looking for, which was a black marker. I do have a green marker, which I don't think that's gonna work. A red marker, which it may work. So let me try to get some order for this marker thing. All right, so this is the final part of the lecture for tonight. And what I want to do is talk about first about what is RMS. And then I want to show you a different form that you can write AC quantities in. So we're going to answer the question now, what is the meaning of RMS? Now, RMS stands for root mean squared. And what they did is they took the R from root, they took the M from mean, and the S from squared, and that's where they get the RMS from. Root is a square root, mean is a kind of average, and the square sum means you raise it to the second power. So there's actual formula that they use to get an RMS value, which is think of it as a special kind of an average. But when I say what is RMS, I mean physically what is it? When you say that you have an AC voltage or current, so many volts RMS, what exactly are you saying? So to start the conversation, I want you to think about what happens to you when you work really, really hard. And I don't mean work like doing schoolwork or go to work. I mean like you have some kind of activity you're doing, and you work really hard. So maybe you're cutting the grass, maybe you're jogging, maybe you're exercising, you're doing that kind of work. What happens to your body when you do that?
You sweat?
You sweat. Why do you sweat? What's your body trying to do?
Because you're burning calories.
You're burning calories, you're sweating, you're getting hot. So the idea of sweat is to keep your body cool so it doesn't overheat. Because what happens is, as you do a lot of work, you're turning joules of energy in your body to joules of heat, so you're sweating. And the idea of sweating is to keep you cool. Now, I don't know if you know this or not, but dogs do not sweat. You guys know that? Dogs don't sweat, so to get rid of heat, what they do is they pant. That's why they pant like they pant. So some animals don't sweat. So biological systems, you sweat, or you have some means of keeping yourself cool. Maybe birds might open up their wings to try to keep themselves cool. I don't know. But when we talk about mechanical work, let's talk about mechanical work. Mechanical work. And mechanical work is what happens when you have anything that moves. You have a force, and that force acts on the object to push it, to translate it, to rotate it, to spin it. Any kind of motion where there's a force involved, that's electrical work. And so like a motor running, it's doing electrical work. Anytime there's a force that acts through a distance, you're doing, I said electrical work, I meant mechanical work. So I want you to think of a machine, any old machine or device that's doing mechanical work. Now, when I say mechanical work, it doesn't have to be a mechanical object. I don't mean mechanical in the sense that you have moving parts. I mean mechanical in the physics sense. So as opposed to going to work or you're doing biological work. So like when you turn a motor on, if you put your hand on the motor before you turn it on, and then after you turn it on, it's going to heat up. If you have your cell phone charger in your hand, you put your hand on it, it's going to be at room temperature. But when you plug it in the wall so that you can charge your cell phone, it's going to heat up. Early this morning, I was supposed to meet a contractor and I went over to the shop where the contractor works, and there was 2 vans parked out in front of the building where the contractor works, and the door was locked. And I said, I wonder if this guy's in there. So I went over and I put my hand on the hood of the car to see if it was warm, because if the car had been running, the engine would have heated up the hood, but it was cold, so I figured, well, the car's been there all night. But the point I'm making is, your gasoline engine gets really warm because it's doing mechanical work. Well, it turns out when we talk about mechanical work, it will produce exactly the same amount of heat. Here's what I mean. Let's say you have a motor that does a certain amount of mechanical work, and I have a cell phone charger that does a certain amount of mechanical work. Now, the cell phone charger doesn't have any moving parts in it. It's just a transformer, rectifier, all the stuff, the electronics that go in to make a charger. The motor actually has a magnet, the coil, and it's spinning around. But let's say in spinning around and doing electrical work, let's say that the motor temperature went from 20 degrees C to 100 degrees C. And let's say the cell phone charger, which is a totally different kind of a device, it's no moving parts, it's just resistors, capacitors, diodes, whatever's in the package. Let's say it went from 20 degrees to exactly the same temperature when you plugged it in, 100 degrees C. If both devices, the motor and the cell phone charger, if it went up the same number of degrees, then what that means is that both devices are doing the same amount of electrical work. You can tell how much work something's doing, this kind of work, mechanical work, by looking at the temperature of the object. How much did the temperature increase? If I have 2 different objects, I could have a car engine and a cell phone charger, or I have any 2 objects, if the temperature change is exactly the same, then what I know is that each one's producing the same amount of work in the form of heat. Now, if you follow that, let me explain what we mean by RMS. Here's what is meant. So what I'm going to do is I'm going to draw, we would do this with an experiment, but you're not here. This is not a chemistry or physics lab. I'm going to draw the experiment on the board. We're just going to use logic to figure out what will happen. So imagine that I have got a pan of water. And in the water, I'm going to put a resistor. I've got a switch. I've got a battery. And just for the heck of it, we'll make it 100 volts. Now, I also have a thermometer in the water. I can take the temperature, I can measure the temp. And with the switch open, the thermometer reads this. It starts off right here. And you can't see that. And then what I'm going to do is I'm going to close the switch for, let's say, 20 minutes. So I close the switch for 20 minutes, and what's going to happen is current's going to flow through the resistor. It's going to start dissipating power, which means it's going to heat up. That's going to heat the water up, and the temperature is going to go from here to here. And it just stays there. So after about 20 minutes, I open this back up. When I open it up, current stops flowing. Eventually the resistor is going to cool down to where it was before. And the thermometer is going to go back down to the starting temperature, whatever the room temperature is. Then what I do is say, all right, I'm going to take this off. And instead of a battery, I'm going to have an AC source. Now, you guys haven't seen AC sources yet, but in electronics, this right here is a battery. This right here is a cell. If I have it like this, that's an AC voltage source. So instead of having the battery, I'm going to put the AC source over here. Okay, so this is volts AC. But the other thing I'm going to do is I'm going to put a line through this source like that. Does anybody know what that line means? When I put a line through a device or source, what does that mean?
Variable.
That means I can. That means I can
change.
I can change it.
Yes.
I can adjust.
Adjust.
So like,
Adjustable.
if I have this, that's a fixed 12 volts. If I put an arrow through it, that means I can change it from 0 to 12. So I'm gonna put an AC source here, but I'm gonna actually make it variable. And I'm gonna turn it all the way down to 0 volts. So right now it's off, and then I'm gonna close the switch. And when I close the switch, what I'm gonna do is I'm gonna start to turn the voltage up really slowly. So I'm gonna turn it up a little bit, and what's gonna happen is the AC is gonna go back and forth, back and forth, back and forth. The DC battery, the current went one way, and it caused the resistor to heat up, and the mercury went up to the end tip. But here I got alternating current. It's gonna do exactly the same thing. Current is current. The resistor don't care what direction it's going. It's gonna cause that resistor to heat up. So I'm gonna turn this up a little bit, and the mercury is gonna go up a little bit. I'm gonna turn it up a little bit more. Mercury's gonna go up a little bit more. And what I'm trying to do here is I'm gonna slowly increase the AC voltage source until the ending temperature of the AC source is exactly the same as the ending temperature of the DC source. So I'm gonna keep on turning this up until it gets to where the DC source stopped, which was right here. At that point, what do I know about the AC source?
It's doing exactly the same work as the DC source.
And that is the key, what he just said. I know it's doing exactly the same amount of electrical work as a DC source, which means I can treat it as if it's DC, because the resistor doesn't care. When we talk about heat, there's AC current, there's DC current. There's AC voltage, there's DC voltage, but there is no AC or DC heat. It's just heat. So when I look at these voltages in terms of heating effects, it doesn't matter if they're AC or DC, it's all the same, if that makes sense. So what you're saying when you say I have a source, say you got a voltage source, an AC voltage source, you say, all right, it's 100 and this marker is terrible. Say you got an AC voltage source, it's 120 volts RMS. What you're saying is effectively it's doing the same amount of electrical work. If you put RMS on it, you're saying effectively it's doing the same amount of electrical work as a 120 volt DC battery. So RMS renders AC and DC equal to each other, because now we're not looking at whether the current is going in one direction like in DC or whether it's going back and forth alternating like in AC. We don't care because we're not even looking at voltage or current. Now we're looking at the amount of electrical work being done. It's kind of like when you tell your kids, look, I got this work. I don't care how you do it. The end result is I just want it done. I don't care how we get to this temperature right there, whether you do it this way with AC or this way with these, I just want to get to that temperature, that amount of work. So RMS is special because it renders AC. I'm not saying that they're equal because it takes more AC voltage to do the same amount of electrical work as DC. But I'm saying that when you write it in RMS, then you're saying, all right, this is an equivalent amount of DC. 120 volt AC signal RMS has the same heating effects as 120 volt DC battery. And since we're looking at heating effects, I can treat the AC as if it were DC. Now, you don't know what I mean by that, but you will. So that is really, 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 that's three reallys, important. Okay? So I told you that the other term for RMS is the effective value. And I told you I like that value better. Instead of saying 120 volts RMS, you say effective value. Effective DC value is what they mean. So RMS is the DC equivalent heating effects, which means that that DC battery and that AC source are doing the same amount of electrical work. Okay? So if you think you follow that, the next thing I want to do is talk about phasors. Now, we already talked about phasors, but remember our definition for voltage was that, and I can add the phase angle if I want to. So you might have something like V equals 100 sine 377t. Well, in math, y equals 3x plus 1. If I have that in math, then this right here is called my domain. And this right here is called my range. The independent variable x, whatever numbers you're allowed to put in for x, is called the domain. And whatever number you get out for y, those numbers are called the range. Well, here, the domain is this. My independent variable is not x, it's t. And my dependent variable is v. So since the domain is t, they call this form of AC, they call it time domain. Time domain. Well, what I want to look at tonight is we're going to look at phasor domain, and I think it'll become evident why we look at phasor domain. Okay, so that's going to be the next thing. So, just to make sure you're clear, if I have 120 volts RMS, that means that this AC source is doing the same amount of work as a 120 volt DC battery. Now, how much peak voltage does it take to do that amount of work? How would you figure that out? Because AC is really a sine wave, it's really a peak voltage, but how much peak voltage of AC does it take to do the same amount of work as a 120 volt DC battery? How would you figure that out? What would you do?
Multiply by 0.707.
Right? So if this is the equation, well, they gave us this, so I put in 120 volts. So what I want to do now is, given 120 volts RMS, how much is that in peak? So I'm going to say that peak is 120 volts divided by 0.707. What's 120 divided by 0.707? 1 what? So 169 point something like that. About 170 volts. So it takes about 170 volts of this to do the same amount of work as a 120 volt DC battery. If you understand that, then that's the meaning of RMS. Okay? Anybody have any questions over the RMS story I just told you. Questions or comments? All right, well, let's go to the final topic sheet of the night. I'm surprised I still got 9 people. I don't know if I really have you because you could have your screen on and you could be in the bed asleep right now. I don't know. But my machine is, Michael, you have a question?
No, I'm telling you that I'm still here.
You're telling me what?
I am.
Oh, you're here? Okay, so I know Michael's there. The rest of you could just have your computer on and you could be in the bed asleep. So Michael's proving that he's here. Okay, look at this document, guys. This is the last one for tonight, and then we'll get out of here. So, we already kind of know this a little bit. Let's talk about phasors. A phasor is a rotating arrow fixed at the origin of a coordinate system. We talked about this a couple weeks ago. The projection of its height on the y-axis in any instance will give the corresponding instantaneous value of the voltage of the sinusoidal waveform. All that's saying is that in that packet I gave you where they showed you the phasor going around in the circle, that phasor was turning counterclockwise and it traced out a sine wave. And it's just saying, depending on where the phasor is, that has a direct relationship to what the instantaneous value is at the point of where the phasor is. Now remember, the phasor is telling us where the generator is in the magnetic field as it spins around 360 degrees. So the bottom line is, you know, a phasor is a rotating arrow whose tail is fixed at the origin of a coordinate system. So now it turns out, now this is important right here. It talks about phasor algebra or phasor math. Now this is very important. It says that phasor algebra for sinusoidal quantities is applicable only when waveforms have the same frequency. So in other words, in this class, anytime we're dealing with phasors, all the phasors have to have the same frequency, which means that they're rotating at the same rate, which is most of the time that's true, because usually you have one generator generating voltage. You don't have more than one generator turning at 2 different rates. More often than not, you have one generator hooked to a circuit, and it's going to send voltage and current all the same frequency. But if you had 2 generators traveling or moving at the same different angular velocities, different frequencies, then you couldn't apply any of the stuff we're talking about. But you won't have that situation in this class. So I want to talk now about phasor form. Let me get off camera. Let me get on the camera. Let's talk about phasor form. So there's time domain, and then there's phasor domain. So if I want to write a phasor, it's really simple. Phasor form or it's called phasor domain. What you do is you write the number, and then you'll have a phase angle. So this number right here has got to be an RMS value. And then this is the phase. So what you got to be able to do is go from time domain to phasor domain. So how do you do that? Well, it's actually pretty simple. Right here you have the peak value. You take the peak value, you multiply that by 0.707, and that's what you put right here. That would be the RMS value of the phasor. And the phase angle, if you remember last class, we said that there was actually a plus or minus beta here, and that was the phase angle. I don't think you can see that green. So, given Given the AC expression in time domain, you want to convert it over the phasor domain. You take the peak value, multiply by 0.707. That's what you write here. And then whatever the angle is there, that would be the phase angle of that phasor. Now, phasors actually rotate around in a counterclockwise direction. When you draw a phasor on a coordinate system, it's like you just took a snapshot of it and it's not moving. I'll mention that in the later class. But you got to be able to go from time domain to phasor domain. Now, why do I want to go to the phasor domain? Well, the reason I want to go to the phasor domain is because this value right here is an RMS value. What is an RMS value? An RMS value is just an AC value that gives me the same heating effects as that number in DC, which means since I kind of changed voltage to heating effects, and there is no AC or DC heat, there's just heat. So that means whatever I can do in DC, if I have the AC and RMS, I can do exactly the same thing. I can do Ohm's law, I can do Watt's law, I can do Thevenin's theorem. Whatever I did last semester, I can do it with AC as long as I write it as a phasor, because AC renders that RMS value is the same as the DC value in terms of heating effects. So this diagram here, the paper, is some practice doing that, going from time domain to phasor domain. So look at this first problem. They want you to convert from time domain to phasor domain. So get a piece of paper out if you don't already have it. And I want you to do problem number 1, problem number 2, and problem number 3. And then problem number 4, we'll do this one next week. We'll do that next week. So do these 3 problems based on what I just said. And then we'll call it a night. So I think what we'll do the first one together. I'll put it on the board and we'll do that one together. All right, so for that very first one, here's what I have. I got script V is equal to 50 sine omega t. That's the peak value. Now notice they didn't give me a number for omega. I don't need it. When I'm going from time domain to phasor domain, I don't care what the angular velocity is. So all I got to do is I got to convert the peak value to RMS and then write the phase angle over here. Well, I don't have anything written over here, so that it'll be plus or minus 0 degrees. So what I got to do is take 50 and convert that to RMS. So VRMS is 0.707 times V peak. But in this case, the peak value is 50. So somebody take 0.707 times 50 and tell me what it is.
35.35.
So this is 35.35, and my phase angle will be 0 degrees. Now, let me show you the notation we're going to use in this class. If you see a lowercase b or a lowercase I, that means it's an instantaneous value, and it came from a sine function, right, like this. But a phasor, the way I'm going to write it is I'm going to use an uppercase letter. So instead of writing this, I'm going to write that, a capital letter. And then to show us a phasor, I'm going to put this little mark on the top. That's called a hat. So to show us a phasor, I got to show it that way and then put the units. This would be volts. And what I usually do is put brackets around my units so I don't confuse that V with that V. You see it? So to do the whole thing, convert time domain to phasor domain, and then make sure you put a hat on the unit, and it should be capitalized on the symbol, and then put the units. So if you think you understand that, let me give you this. I'm gonna give you a couple minutes to do it. And then, well, that's the wrong one. And then we will call the night. So do number 2 and 3, and we'll do number 4 later, next time. I'm gonna give you about 1 more minute, and we'll talk about these 2 problems. And then I got one more thing I want to share with you, and then that'll be it.
Your sound.
I keep forgetting about that. So I want to convert this to a phasor. I want to take the peak value, convert it to RMS, and then write my phase angle along with the RMS value. So you're going to multiply this by 0.707 to convert it to RMS. If you do that, what do you get?
$49.42.
How much?
49.42.
Okay, so that would be my voltage, and this would be at an angle of 30 degrees. And if this was a voltage, you would write it like this. If this was a current, you would write it like that, and then put the proper units on it. Okay? So all we did was multiply my peak value by 0.707 to get it in RMS, and whatever's there is my phase angle. Now this one you gotta be careful. I don't know if you got that one or not, because it's something you gotta think about. Anybody know what this is? What's this? What's the difference between that and this?
The left one is phase shifted 90 degrees.
That's true. She said this is phase. See, this is right here. That point right there, we know that that's 90 degrees. So that's phase shifted 90 degrees. So she's right. But what kind of wave is this? This is y equals what?
Sine.
Do you know what this one is?
It's cosine.
Sine.
Y equals cosine theta. If you learn your trig, that's a cosine wave, that's a sine wave. Now remember what Mandy said. She said, well, all that is a sine wave shifted 90 degrees. So if I take this sine wave, now how do I shift it 90 degrees? Well, I gotta take the angle and I either gotta add 90 degrees to it or I gotta subtract 90 degrees to it. If I want to shift it this way, I want to shift it that way, do I add 90 degrees or do I subtract 90 degrees?
Add.
I add. Last week I told you to remember that because it's the opposite of what you might think. I'm going to add 90 degrees. So if I add 90 degrees to a sine wave, then what I get is a cosine wave. So in other words, you see this right here? I can write this like that, or I can write this like this. This right here is equal to 45 sine omega t if I add 90 degrees to this. So you can convert a sine to a cosine. Cosine theta equals sine theta plus 90 degrees is the trig thing you would use for it, the trig identity or whatever they call it. So what we do is the cosine wave, we convert it over to a sine, and then we can do exactly what we did over here. We just get my RMS value and my phase. So what is 45 times 0.707?
31.8.
And there you go. Now, there's one more problem on the sheet. I'm going to do that next class. But why don't you give it a shot? If you think you understood everything I talked about tonight, give that a shot and see if you can come up with the answer for me. And if not, I'll work it next class, and you'll see the last one. Now, I have one more thing, and I promise this will take about 3 minutes to show you. Does anybody know what a Venn diagram is in math? Does anybody know what that is?
I just remember intersection and union.
Yeah. So you've seen them before. It's like you might have something like this. So you might have set A, set B. This would be the union of two sets. You might have them like this, and they might not intersect. But what I want to show you is this. You don't even have to know the term Venn diagram. I'm going to give you a Venn diagram, and I want you to tell me what I'm trying to say with this Venn diagram. Here's my Venn diagram. I don't like this green. I'm having the hardest time with markers. Okay, so here's my Venn diagram. What does it mean? Explain that.
All phasors are complex numbers, but not all complex numbers are phasors.
Exactly right. I mean, if you've never seen this before, if you look at it long enough, anybody with the IQ of a donut hole can see eventually that's what that's saying, right? Like if I have, this is the complex numbers. All phasors are complex numbers, but not all complex numbers are phasors. So if I can have something here, and that's a phasor. I can have something over here, it's a complex number, but not a phasor. If it's a phasor, it's a complex number, but because it's a complex number, it doesn't mean it's a phasor. It's really important that you understand that. Now, I'll say more about that next week, but here's what you want to know. The only phasor quantity I can have in AC, and I'm starting to lose my voice because it's getting late. The only thing in AC that can be a phasor is a voltage or current. And that should make sense to you because in order to have a phasor, I got to have a peak value because I got to take that peak value and convert it to RMS. There is no peak resistor value or peak capacitor. Only thing that can be peak is a current or a voltage. So if I have a phasor, it's going to be written in RMS. The reason that's important is, remember when we converted the numbers just a second ago from the sheet, I told you might have something like 50 at an angle of 35 degrees. But that's a phasor, so you'll put the hat on the V like that, and you'll put the volts like this. So there's my phasor, and there's my phase angle. Well, that looks just like a complex number in polar form because it is a complex number. It's just a special complex number that's a phasor. But because it's a complex number, you can take that voltage and write it in rectangular form because you can write any complex number in rectangular form. That's important because what we got to do in this class, remember, we'll do the same thing you did in DC. You start out with just a resistor and a voltage source. Then you get a series circuit. Then you get a parallel circuit. Then you get a series parallel circuit. But it's way more complicated than DC because everything is moving as a sine wave. But since we have phasor notation renders AC and DC equal. So whatever I'm doing in DC, I can do exactly the same thing with the AC waveform, so long as I don't show it as a sine wave, so long as I show it as a phasor, because now we're dealing with heating effects. And there is no AC or DC heat, there's just heat. You don't care if the heat is flowing back and forth or just flowing, you're going to warm up the same way. So if it's a phasor, I can write it in rectangular or polar. If it's a complex number, I can write it in rectangular or polar. That's important because When I'm working the problem, if I have to add phasors, I got to do that in rectangular form. If I got to multiply phasors, I got to do that in polar form. The same with just regular complex numbers. So tonight, I talked about quantities that are phasors. If it's a voltage, I can have a voltage phasor, I can have a current phasor. Those are the only two kind of phasors that exist in the electrical world. Any other kind of complex number is not a phasor. And next week, we'll talk about, well, what are the other ones that's not phasor? We'll talk about that next week. Okay? Oh, guys, this is the longest class. We're just like less than 10 minutes away from the whole 4 hours and 20 minutes. So those of you who stuck with me, I appreciate it. I just know some of you, I'm looking at the screen, I know some of you just got your computer on. You're not even there. You're just acting like you're there because I can't see your camera. But if you really stuck with me, I appreciate it. If not, you're one of those that just got your camera on and you walked away. At least we got this recorded, and you can go back and listen to the recording. It's important. This is a really important lecture because it's going to set us up for the rest of the semester. So guys, have a great rest of the day. I finally get a chance to meet you next week. So I'm excited about that. Make sure next week that you bring a mask with you. And I will post some things to Blackboard on what I expect you to bring in and about the quiz and all of that. So in between now and then, if you have any questions, please send me a text. Before I sign off, anybody have any questions or comments?
I got a question, but not an important one. When I said I'm using MacBook, you laugh. So I want to know the reason why you laughed.
Well, there's this thing between PC users and Mac users. Typically, engineering students and science students, they use PC stuff. And if you're in the arts, like music, or if you're in like graphic design, that's the Mac world. And I hardly ever see an engineering student using the Mac or Mac-related device. Now, I know a lot of those Macs now can run PC stuff, and I don't think the PCs can run Mac stuff, but it's just unusual to see a Mac person in an engineering kind of environment. Everybody does PCs. Now, you'd have to know that to find the joke funny. But, yeah, for pretty much if you bring a Mac computer to an engineering student, it's like bringing a dog into a cat pound or something like that. So that's all. I'm wondering now, are you able to run PC software on that MacBook?
Yep.
All right, well, let's try something. So you're not able to open up that document. Let me turn this recording off. I don't want to record this.